All right, cool.
Yeah. Do you want me to stream? Do you want me to hit it?
Yeah.
Yeah. All right. So it's loading. It's like halfway through. Okay. Yeah, I think we're good.
Oh, is it live? Okay. Wow, I didn't expect that to work. I figured we were gonna have to call yoga.
Right? Yeah, and I'll pull it up on the, do you have it on the confidence monitor?
I do, yeah.
Gotcha. Cool. Oop.
All right, so sir, we're good.
Yes, sir. Thank you. Yeah, that's cool.
All right. Well, Scott, I'm gonna step away and I'll have this going, but I have my other laptop I'm getting ready to dial into cheese here, who starts at 10.
That's cool. I made you the co-host, and I talked to Daryl yesterday, so I'm anticipating just letting. Uh, well, actually, he's going to come in by the time the meeting already starts. So by like 10:30, I'll take a look for him and then promote him. So we should be good.
All right, sounds great. All
All
right,
right.
well, sir, I appreciate it, and I'm here if you need anything.
Likewise. Thanks, Miguel.
Thanks.
Hi, Malaki. Can you hear me? Can you hear me? Is there anyone that can answer me? Maybe you cannot hear me.
I can hear you.
Ah, okay, perfect.
Yeah,
I
we
can
can
hear
hear you.
you.
Okay, thank you very much.
You got it.
Hi, Malaki. How are you?
I apologize. I was on mute.
Okay, okay. How are you? Everything okay?
It's a nice, beautiful morning on the West Coast. So things are good.
Nice,
Yeah.
nice, nice. You are not yet here in Newport News.
Not yet. I should be there in what is it? Mid-July.
Okay.
So for now, I wake up. For now, I wake up at about 5 in the morning, and
Indeed, I hear your voice that is like of somebody that just wake up.
the coffee hasn't softened my throat yet.
Okay, when you want, we can try it. I think you can share your slide just to check, and then we wait that almost everybody will arrive.
Oh, sounds good. Okay, so I guess that requires you to stop sharing the existing screen.
I'll take care of that for you.
Looks like it's already been done. All right.
Alex, is Amber not going first today?
Alberto, I don't know where he, so I don't know.
Okay.
I mean, if you can manage, I don't need to be the co-host actually. If you can manage this,
Yeah, that's cool.
It was actually very easy yesterday, so we had no problem at all. So
Gotcha.
thank you very much.
No sweat.
Hello, good morning.
Hey, Juan.
Hey, Alex. How are you?
I'm good. I'm good.
Hello, Scott. Hello, Miguel.
Good morning. How are you?
Good, you?
Good, good. So do you want to try to put the first slide up from the presentation? There you go.
Oh, nice. Nice.
That looks good.
Sorry. Yeah. All right. So that worked. I was
Yeah,
having a bit
yeah.
of a.
So I'm looking at the, it looks like it's in a presenter view. I see the thumbnails on the left, if that's okay.
Sure, sure. Yeah, I'll change that. Let me
Gotcha.
just wipe this up to a new desktop.
That looks good.
So, all right. Yeah, I wasn't sure what aspect ratio you guys were expecting, so hopefully this is adequate.
Yep. Yeah, I like the way that looks. It's cool. It's in
Yeah.
the center and I have just gray boxes on the side. So it looks like
Yeah.
I'm getting the full slide.
It's
All
good.
right.
All right.
Very
I'll be
good.
here if you guys need me.
Thank you very much, Scott.
Thank you.
Okay. Just wait. Let everybody wake up, actually.
I don't want to hear about anybody on the East Coast saying they have to wake up.
Oh, it's Alberto. Also, Alberto is here, so. Hey, hi, Alberto.
Hello, I was muted.
Ciao, Alberto.
Good morning. Hey, Scott. Good morning.
Good morning.
Not many people. Well, we have to start at about in time.
Yeah, I'll just wait other 4 minutes and then we can start. I mean,
No, this year we are really to stay much more on top of our times.
but yesterday it was quite good, I think. I mean, we managed to go out just for 5 minutes in the afternoon, I think.
No, more than that, 10, 15.
Okay.
We ended up at 4:15, but there was a couple of delays there.
Mm-hmm.
We just
Oh, I should be able to make up time. That's
No,
just a lot of questions.
It's we physicists are not good, in particular to stay in our times. We are too anarchic, as you may know. But stop.
So now we've all been warned that we're recording. That's good.
So this started the conversation completely.
Yeah, everything stops.
I can pause the recording for you. Yeah, if you want, you just let me know. There you go.
No problems.
I haven't
know-
signed the disclosure, so you
It's,
can't record me.
I think we're streaming currently, though. We are live streaming.
Okay.
So
Well,
I'll
good
start.
thing we're saying we haven't said anything inappropriate, so that's very good.
Just a heads up.
Right.
I will at 10 o'clock. I'll start the stream, and I'll restart the record, and I'll let all the folks in. Or I'll start the webinar officially.
Okay.
Yeah. Okay. Thanks.
You got it.
Actually, Scott, how long do you need? Do you all need to put recordings online?
I'm not sure what the turnaround time is for that. I know that the stuff that's landing on the YouTube page isn't taking very long to show up.
Okay. Well, we'll see. We'll monitor them. It's great. I like very much on this. And at some point, I will ask you all how many people were in the back.
Yep.
I guess not a few.
Yeah, we should get a number of participants once we actually start the webinar. We'll be able to see how many attendees we have. Currently, we're 36 on our side.
Yeah.
We should also let the students know to maybe to join 5 minutes earlier or so at least. Maybe we can also give them a couple of school announcements before we start. I don't think.
All right, you know what I'll do then? It's 1 minute till. I'm gonna open up the webinar. I'm gonna let folks in.
Very good.
Okay. Thanks.
I just threw a message on the Slack telling them that the lecture is about to start, that they should enter.
Yeah, but they are quickly growing, so we are already at 45.
And I'm going to start the recording.
Just-
Okay, it's 10 a.m. So we are 46, Alberto. What do you think?
Yeah. We go on.
Okay.
It's 10 a.m. We start.
Okay, so thank you everybody for coming in this second day. I'm very happy to see a lot of people also today. I hope that they will grow in the next few seconds. And I want to introduce our first lecture of today, that is Malakai Shram. He's the head of the data science department. He's just hired this year in Jefferson Lab. And I went through his CV just yesterday. It's quite impressive. I have to say that it looks really a a very good scientist in artificial intelligence and machine learning. He's the leading research here at Jefferson Lab for these things. So I hope you enjoy his lesson, and I'm really interested to listen him. Please, Malachi.
All right. So, well, thank you very much. And I really appreciate the opportunity to present at these sessions. I'm very excited to try to share some of the things that I've experienced, and hopefully we'll have some very fruitful discussions and possible future collaborations. So again, I really appreciate this opportunity to talk to everybody and show some of the work that we've been doing. So just as a very high level summary of maybe my CV, or not quite, but since I'm so new to the area and also to JLab, it's been about a month. So my research of interest, or my prior history in the last few years, has been predominantly on distributed computing, which I'll talk about today, design and control, specifically applications of reinforcement learning or Bayesian optimization for various applications, either accelerators or water material discovery. And then various types of applications as it pertains to machine learning. So anomaly detection, prognostication, segmentation, object identification, classification, few-shot learning, things like that, just traditional things. And of course, adding a bit of the domain-aware ML component. So for today, I'll be pretty well talking about my experiences in distributed computing as it pertains to Bell 2 and also Project 8. And again, the intent of my talk is really somewhat casual, and I'm hoping that as questions arise, please feel free to just raise a hand. Hopefully I'll be able to see it in my screen. And from there, just feel free to ask me a question as we're rolling along through the slide deck. Definitely, it doesn't have to be a very formal presentation. So with that, I'm going to start with the first slide, which is what is distributed computing, or in this context specifically, what is grid computing? So, at the highest level, if you will, it's really a coordinated collection of geographically distributed computing resources that is there to really enable new scientific discovery. So it's a way to essentially aggregate additional resources. So what you see in this figure at the center point is what we would consider a centralized system that kind of coordinates the activities of this distributed computing environment. In the illustrations in the clouds, you have a cloud resource here. Hopefully you can see my mouse. And then you have these traditional resources in the square boxes. You'll notice that within the depiction, what you see in the center box, which is a central server, it communicates to all the resources through these red lines, through the wide area network. But it should be noted that there's these black lines that are also communicating across the various resources. So in reality, in practical, I couldn't draw all the lines. Obviously, all the components are really able to talk to themselves through various proxies, okay? And so what I'll do is I'll kind of work through the process of how this actually works out in reality. But this is just a high-level schematic view to illustrate conceptually what it is. And as you can see, conceptually, it's a fairly easy idea. Implementation is substantially different, and you'll see that there's a lot of technology that goes into this process, and I've only skimmed the surface of the topic given the time that we have. So I'll move to the next slide, which is a real-world application, and this one I was actually explicitly involved in. This is a Bell 2 illustration where I led the US contribution for this international project. So what you're seeing in this figure is a distributed computing. It looks like probably a mess to everybody, and let me kind of get your bearings. So in the previous slide, that centerpiece here would be this DIRAC server. That's the orchestrator of your distributed computing infrastructure, all the resources. What you'll also notice and hopefully you can see again my cursor, is that you have this virtual DIRAC interface to some cloud computing. You have this CREAM CE, which is using what's called dynamic torque, interfacing with, again, some more cloud resources. Another site at UVic, which is just near where I am, which is using HD Condor, is also using cloud resources. And then the P&L site had Slurm and also HD Condor accessing some cloud resources. What you'll see is Slurm or HD Condor or Dynamic Torque, all these wordings, those are really the schedulers that submit the jobs to the local resources. But you need to have some way to coordinate that across the different resources into a central area. And this is this DIRAC software stack that allows you to do that. What I wanted to convey with this figure, though, is the vast, the wide variety of these interfaces to the local resources. And also how some of them are going to run on bare metal. So they're going to submit jobs to just normal hardware clusters. And some of them will submit jobs to cloud resources. So you really have this really wide heterogeneous resource allocations component that you have to consider when you're doing this. On top of that, every region has their own funding providers that will enable certain implementations of various types of interfaces. So we have in the US what's called Open Science Grid, or we had that allows us to have certain baseline software stacks that allow us to do distributed computing. In other regions, like in Europe, they have their European Middleware Initiative, and this evolves, by the way. And so there's all these different components that are kind of tugging at it, at this problem from different angles. And it's really, how do you coordinate this internationally? Because most of the time when you're doing grid computing, it's an international effort. Okay, so that just gives you a bit, hopefully that gives you a sense about the complexity of just, how many resources there might be and the diversity of the resources you will have to interact with. So before we go too deep into the grid computing, I want to just go through this a bit of a step back in a very high level to talk about conventional scientific computing and kind of discuss the sequences that we all do when we access these HPC systems, these high performance computers. But now talking in the context of a user and kind of illustrate the steps that go into this. And then what we'll do is we'll roll this into the grid computing framework. So the first step is that user, that person has a terminal. It needs to have access. It has a mechanism for authentication. This, again, evolves almost yearly now. It used to be just a password protection, a password. Now it has to be a password with some peppering of some other technique. So there's evolving methods for authentication. Once you've logged into your worker node, the login node, which of course requires you to have an account on that machine. It also has to have password and all these setups, your environment setups. But that is really an interface for you to now submit jobs to the queue itself. So all these compute nodes, that's where you're going to submit the jobs to. And to a very limited, and I highlight very limited because I think some admins might get very upset with me if I even suggest that you should do this, but I think we all do. You could do some very limited test runs on this login node. But since most of the people I think online are students, I would take this very seriously. There's nothing worse than having people trying to do fairly large jobs on the head nodes because it really causes problems for everybody else. So please take that to heart. So again, so you have a logging node. It has access through some kind of scheduler, Slurm, HD Condor, Torque. That probably just sounds like jargon, and you probably don't really care what this is, but there are quite a long laundry list of possible ways to submit jobs to a queue. That compute node is this cluster is where we actually execute the computational work. It has a fairly well-defined set of OSs. typically on a single cluster, you'll have one singular OS. You'll have a set of libraries, and then you'll have a collection of software stacks that are either shared through the shared disk, or it could be actually installed on each individual node. Both of those techniques are a bit quirky, and they introduce their own problems. And there are some interesting solutions that have come from the grid that actually are nice to pull back into even a local conventional computing. And I'll talk about that. So finally, you have the storage. Here you could have on the back end something called Lustre or NSF, Ceph. These are, for all intents and purposes, just like your hard drive, but now available to all the machines that are actually located on the cluster. So whenever you run a job and you save files, that's where that would reside. And so that's at the heart of it, at a very high level, a scientific computing framework. Moving forward, the obvious question becomes, okay, well, what should I be considering if I'm going to go from, if I want to do grid computing versus local computing? What are those elements that need to be considered? And I've just listed a few of those just as conversational again, just as a thought process, okay? So the first one is really, what are the resource requirements and how do we make sure we make that allocation? As we discussed, there's this whole authentication element of even a user accessing local resources. But that definitely gets much more complicated when you actually go into having to access multiple resources where you're not actually physically SSHing into your machine. You're now doing this through a distributed fashion. So there's a lot more at play there to kind of coordinate that. So there's an extra level to account for. The computing resource and also the software distribution becomes a little different. And there's things to consider that you otherwise wouldn't have to consider. Data storage, and more importantly, data transfers. How do you move data across the various resources, compute sites? How are you going to manage that? And actually, probably more importantly, is how do you keep track of all these files as they are distributed across the world? How do you know where it was and how do you allocate? So that's another level that you have to account for. Finally, things that you have to consider is once you have these resources and people have said, yes, you could use my site for XYZ, you actually have to coordinate the effort. And so you could write your own scripts and you could use OSG without any coordination by just submitting, as long as you're part of a virtual organization, which I'll talk about. However, it's not a very efficient way of doing large scale computing. So typically you have a fairly well-developed grid orchestration framework. And then I'll just make a little note about workflow automation. I think that's, to me, been a very important aspect of my work in terms of making sure that production runs smoothly and there's very few hiccups. Having the ability to just identify right sequences of processes that are data-driven, so that when new files show up, I don't have to actually manually start submitting jobs, that everything is automated. So I'll talk quickly about one of the implementations that allows us to do this and how it helps our lives significantly. So let's dive into it. So we'll start with some resource estimation, which is the first bullet. And I have a couple of slides to kind of go through the thought process. So large-scale computing and large projects like the LHC, Bell2, and soon to be the EIC, they require an incredible amount of computing. So much so that most of the time this has to be distributed across different countries and geographically. I want to highlight, there's a lot of reasons why you might want to go with grid computing. One of them is clearly redundancy, and that is something that is really important to think about, because what happens, and this has happened, in fact, this is one of the motivating cases for Bell2 going with a distributed solution, is unfortunately what can happen is a site which is significant has an earthquake, for example, which is exactly what happened. And that earthquake essentially decimates the computing facilities. At which point, data that is, raw data, which cannot be just regenerated, you can take more data, but it will never be that data. And taking data is pretty expensive. So when you have a singular site where almost everything is located at, you run the risk of really having the unfortunate opportunity of catastrophic disasters. And so earthquakes are definitely things that have happened, that have taken down like large data centers. Power, UPS power failures, and water, fire hoses. There's so many things that you just do not realize that would happen. In the course of about 5 years, we've seen multiple sites, tier 1 sites, actually have problems where large components of their system were unfortunately extremely badly affected and completely decimated and unable to provide the services they had promised to the collaboration. No fault to it wasn't their fault, but that kind of illustrates the need for this kind of distributed computing, because sometimes it truly is a regional problem, a local problem, as opposed to a computing problem. So with that in mind, this is one of the reasons why we want to do distributed computing. There are other political reasons, financial reasons one would do this too, of course. So in this particular resource estimation, what I'm presenting here is in the left figure is the Bell 2 integration luminosity plot. So the top figure with the green curve. Okay, so SuperKEK-B is an accelerated complex in Japan that is the E+ E-, that is producing rare physics events, and Bell 2 is the experimental detector that is measuring these events. Okay, so one of the things we already know is we have typically with these big projects, we have a sense of how much luminosity, which is effectively how many collisions we're going to have that we're going to register. So how many collisions are we going to actually capture, and how does it scale over time? So here, this is a fairly old figure, but serves the purpose of showing you that as we evolve over time, we increase our integrated luminosity, which is equivalent to, might as well say, our data. So because we know our luminosity, we know the size of an event, that effectively gives us the data volume from the raw data. It also gives us a sense of how many events we will have, and then how much processing we will need for those raw data sets. And also we can estimate based on historical information from, for example, this is Bell 2, which implies there is a Bell 1. We don't call it Bell 1, it's just called Bell, but now we have Bell 2. So there we have the Monte Carlo generator, how you create your synthetic data. And then we have the user analysis, which is by far the biggest uncertainty in these measurements. We also know that Monte Carlo simulations take almost 50% of the compute capacity. So there's always a, hey, how could we leverage the leadership class facilities to run these simulations? So that itself kind of plays into how you actually start planning your resources. And so if you look at the bottom table, at the simplest breakdown is, I need to understand my compute. So this is my CPU. As it evolves over time, I need to understand my storage also as it evolves over time, and my networking capacity. Okay. And that kind of starts dictating what I may need to buy ahead of time, ahead of schedule, because some of these procurements take quite a long time. They're long, what I call long lead time procurements. We need to make sure that we're poised and ready to have the next, 10 petabytes of storage available when it is when the data is coming in. So that gives you a general sense of kind of the high level things that you're thinking about when you're starting to plan the exercise of a new experiment. So if you go to the next one, once you actually have an idea of what are the computing resources, and the fact that you have an international collab. Yes.
Just a thing, there is a question in chat.
Oh, I'm not seeing
are
that. Okay.
actually leadership class facilities?
Why?
What are leadership?
Oh, yes. Okay, very good. So leadership class facilities are specific facilities by DOE in our case that provide HPC resources. So you can think of this as NERSC, which is you can think about this as Titan, or now it's Summit, or you can think about this as the site at Oak Ridge. So we have various centers within the US that are high performance computing centers. And that's what I meant by leadership class facilities. Does that answer the questions, or do you have other?
I'm checking the chat. Gabriel,
Okay.
is that fine?
Yeah.
Probably yes. Go ahead, please, Malachi.
Okay, very good. Yeah, I apologize if I missed that question.
No, don't worry. I'm gonna monitor the chat and also the raise hand, so you can focus on your talk. And I will interrupt.
Very good.
If there is no.
Thank you. All right, so once you have an idea of what the experiment needs, the next step would be to actually come up with coordinating with the network providers, how you're going to actually get data and compute jobs to and from the different sites. So believe it or not, this is actually a lot of work. So you have workshops where the computing sites and the network providers meet. You go over essentially the requirements, and you identify possible pathways, network pathways to transfer the data to and from regions, and how to make sure you have some level of resilience. When I say levels of resilience, there's, for example, at PNL, what we had was we had a major hub in Seattle that went to PL, but we had also a backup connection to Boise. And one of the things we wanted to make sure is if for any reason our network got cut on either the Seattle or Boise side, that we could easily transition to the other connection. So that would just happen automatically. And so that gives you a sense of the type of resiliency we're trying to make sure, because some of the data is coming in real time in Japan. When you're transferring it, and if you're the primary or secondary site, you need to make sure you can actually absorb the data at a reasonable rate so that there's not a massive backlog in Japan. So that's the discussion you talk with the various network providers. That includes ESNet for the US. But we had to talk to our Japanese colleague, establish the Pacific connection, which meant evaluating whether the current infrastructure was adequate, which in fact it wasn't. And so we're going from a 10 gig connection across Pacific, Trans-Pacific to 100 gig Trans-Pacific. And of course, this goes on with the other regions. So what you see in the bottom figures is GAR. So we have this map of how you're going to access data within the two different parts of Europe. And then we typically write these reports. So this is a report that you can have access just to give you a sense of what you might see in a report, which kind of itemizes. This was again for Bell 2, gives you a sense. But ESNet does this with pretty well all the big projects and also all the big programs within DOE and et cetera. So if you wanted to understand how is a network being considered for nuclear physics in general, there's a report on that. So there's reports that are being conducted with the network providers to understand what infrastructure is necessary and when it will be necessary based on the scientific goals of the community. So this is a continuous exercise, and it's a critical exercise because they need to understand what we will need in the future. EIC is no exception. We will have to make this exact exercise as things move along. So now that you have communicated this to the network providers, you can now have a rough estimation of your network traffic. Okay, so this is based on, again, on the site capabilities and the local providers. So even if you had a lot of storage, if you didn't have a good connectivity, it wouldn't matter. You just simply could not engage that site at the level that they could participate at because of the network. So all those things have to be rolled up in consideration. And then at the end of the day, there's there's a level of politics that has to be played too, in terms of, what countries will participate, what fractions is everybody doing their fair share, etc. So those are other elements that get folded into this mix. So that's the kind of the process of kind of considering a large scale distributed computing effort. Okay. Now that we have a game plan, let's start executing. And the first thing you really have to do, at least in my opinion, is kind of establish what's called a virtual organization. So what that is really a dynamic set of individuals or institutions that are going to coalesce around a set of resources. And we're going to define rules and conditions. Typically, when you have a fairly large collaboration, what you'll do is you're going to have an MOU, which is not part of the VO at all, but the MOU essentially establishes pretty well explicit rules in terms of what the definitions of sites, what they're expected to provide, and also what are their expected performance in terms of availability. And so that again, that folds into the expectations of all the collaborators and how you work together. So now that you have created yourself a virtual organization, everybody understands what they're supposed to do. And there's this MOU that is not directly tied to this, but kind of defines everything. You also now need to create in real hardware, this virtual organization management system, which is called VOMS. This is effectively a way for us, it's effectively a database that which is a structured account of the users, the groups, and the VOs, okay? So people across the world can host their own VOMs that says, we are project whatever, and we have these users. All their certificates are registered to this particular virtual organization. And then after that, once that's established, you have the site level, what's called a grid user management system. And this is, again, a lot of this is fluid, and there's a lot of different pieces, but this is how we did it when I was doing this at PNL. So we have a grid user management system called GUMS, and this allows us to essentially turn on what VOs we want to have to give access to for our resources. And so what you have as an example is, let's imagine in the figure, the center of the figure, you have these different VOM servers. You could host your own VOM server, by the way. And so in fact, PNL hosted their own. A lot of people host their own. And what that is again, that list of things that manages the particular permissions for those users in the groups. And let's say site A, which is to the left, what they're connecting to VOM server Y and Z in red, and that will allow users from that particular virtual organization to have access to those computing resources. Okay. Oh yes, thank you for defining MOU. I apologize. And then likewise, site B might have chosen to give access to X and Y. So again, this is just yet another mechanism for people to be able to go out and grab information from a VOM server and then put that into a coordinated area, which is the GUMS. And then all your gateways need to kind of receive information from the user as far as their credentials and cross-validate it to the GUMS server and then you can decide whether, after you've done all this cross-validation, yes, in fact, this user can run a job on my site, okay? So that's a key component of establishing your grid center. So the next thing I had mentioned earlier on was the computing resources software distribution. So there's a couple elements here, and I'll just go through them. So the first thing you have to have is a gateway node, which is really the access point for information to be exchanged between the central system and the local cluster, okay? It could also serve as a proxy for the worker nodes to access the outside world, because that is not a guarantee. A lot of local sites do not let the workers, the compute nodes, see the outside world at all. And so if you don't allow that, then you need a mechanism to be able to transfer that information to and from the outside world to access various components of your grid workflows. And so that is another element that is critical for the compute element, the gateway node. And then it also enables the push-pull or the push, it should be push or pull techniques, depending on what kind of grid orchestration you're using. Nowadays, pretty well everybody's using a pull technique, but that's not exclusive. So the worker nodes are very similar to what you've seen in a local node. The only exception is, again, as I mentioned, this network connectivity, access to the outside world to be able to pull job payloads, and also to be able to have the bright software requirement. Because remember, the now that you have a project that is part of a distributed effort, you need to find a way to make sure that the software is the same across all platforms or equivalent. And so that's where the software coordination comes in. You have to have a well-defined, what is the OS that this collaboration will use? What are the libraries that they need? What are the compilers? What are the domain-specific software stacks? And then if by chance you're a big enough site, you might have multiple VOs that you're hosting, and they each might have very different competing requirements. This is a complete nightmare sometimes, especially if it's really hard set requirements. Sometimes you just have to fracture your cluster, or you could come up with some better solutions, and I'll talk about that later. But nonetheless, that definition has to be really agreed upon across all the sites and enforced. And that also goes with, how much storage do you have? How much memory will you provide? All these little things have to be accounted for when you're doing these sites. In terms of sharing the actual software stack, what's becoming pretty well the common de facto technique is this CVMFS, or the CERN VM file system. And so I've put a link, and throughout the talk, I'll put as many links as I can to all the different technologies, so that if you're interested in looking into it, you can. But this is actually a really, really nice technique where you have what's called the Stratum 0, which is a centralized location for your data, your software repository, effectively. And this is where you compile the binaries, prep everything up for the different architectures that you're going to access. And then you have what's called a Stratum 0, which is effectively a full replication of just a read format. So you cannot modify these things. It's just a pushed copy from the Stratum 0. The next layer behind that is going to be your grid servers. Those are essentially partial caches of your Stratum 1 based on the requests and the data traffic of the request. So if, for example, I need to access software A and I'm on site B, it will first go to the local cache, which is a client cache. If it's not there, then it'll go up to one of the squid servers. If it's not in that cache, it'll go up and up until it hits the Stratum 1, and finally up to the Stratum 1. So what that does is you have this very nice tiered caching system that scales very nicely, and it's pretty easy just to add one or two more squid servers to kind of buffer this the needs for different software stacks. It also works really, really well when you're using the same software across your production job, which is usually the case. So again, if I'm running, one or two software stacks, once it's cached on the client, it doesn't have to go out there again and get the data. So you've really reduced the amount of data being passed to and from within the network. A lot of it actually stays internal to your site and nothing moves. So this was a really, really clever idea. It works really, really well. And of course, squid servers are things that you see in atypical websites. This is, an industry standard. The other thing you can do is these containers. I think everybody's heard about this. And the nice thing about the containers is it allows us to really decouple the hardware level OSs. So what their compute nodes are running versus what the project or the project requirements are. So I could run maybe a CentOS 6 OS, but if the project needs a CentOS 8 or whatever it might be, as long as they create that container, we can actually place it onto the server. And usually the overheads are extremely minimal. So in fact, this is one of the techniques we adopted simply because of some of the limitations of how, if you have a big enough cluster, it's really hard to have everybody migrate to a new OS because a lot of softwares need to be validated. And if you have a large amount of clients, that becomes a big, big challenge. The simpler solution is really to use a container on top of that bare metal And so then it's available. You could change it as you go. And finally, another approach, kind of the hybrid approach, is that you put the containers in CVMFS so that the container is available through the stratums, and then you move forward. So now moving on to the data storage and transfer bookkeeping. So similar to the gateway node that you saw in the compute, we have the equivalent in the storage, where you have a storage element that is used to communicate with the local storage and coordinate the data transfers. We have dedicated data transfer nodes. And those data transfer nodes, at least in our applications, have been managed through grid FTP data transfers. From there, once you're transferring data to and from various sites, you need to start keeping track of exactly where the file is and where its name, its path, what site it's on. So there's usually some form of catalog system that captures this information, and you have to coordinate it. And then you really don't typically use the full path name of a file at site A. You typically have what's called a logical file name, which is just the name, the name that is common throughout the sites. And then the specifics of the site are something that is configured on the back end, so that people don't have to think about, well, if I'm on site A, it would be path this instead of path that. It's just one path name, and then you say use site A, and everything else is done in the backside, so that users don't have to think about exactly what the specific path is. When we're transferring all these data, there's a couple of technologies that are available. Globus Online is something that's really nice if you're an end user that just wants to grab some files and you know what the endpoint is. So if somebody says this is the site for the regional area, on the East Coast, and they give you the endpoint information, you could then simply say, I want to grab these files and transfer it to my laptop or wherever. And Globus Online is perfect for that. When you're actually doing larger scale production work, typically you want to have a little bit more control over how the mass data transfers are working. And so CERN has done a great job at creating what's called FTS3, or the File Transfer Service 3, which allows you to essentially have third-party data transfers, so end-to-end. And you could also do what's called multi-hopping, where you could say, I want to transfer the data from site A to the B to C, and maybe to D. So you could do multiple trajectories, and you start doing some pretty clever stuff. The next thing that you could do also that you have to establish is a network monitoring system. So ESNet's done a great job here, and they're partnering with their equivalent counterparts in other regions of the world. So there's PerSonar that allows you to monitor the network quality across the different sites. So you have to have servers on every site that have this PerSonar service. They ping each other and they start accumulating information about how well the data is going back and forth from these various sites. And then you have what is called a mad dash, which is effectively an aggregation of this information that allows you to understand how site A is communicating to site B. So if you look at the figure that I'm showing to the right, that's a heat map effectively of the sites. So I've clipped the x-axis just because of the size of it, but it's exactly the same as the y-axis. And of course, you don't expect this matrix to be symmetric, because it's two directional. So the top matrix would be in to out, and the bottom would be out to in. So it's going opposite ways, so that you could, sometimes what will happen is the network will work from site A to B correctly, but from B to A, it doesn't. And that's just because the routing paths are sometimes different and they cause headaches. And so you can definitely identify with these tools where you may or may not have problems with your data traffic and data mobility. So then you could try to start addressing or rerouting some of the data to avoid problem sites until they're resolved. Another thing that has to happen when you're doing these large-scale grid projects is really running what are called network data challenges. These are running large transfers between two sites for data stability to ensure that there's no problems between the different DTNs. So these are the data transfer nodes. A lot of times what you'll see is in this particular figure, The y-axis is the data rates, the x-axis is time. And what you're seeing is this nice flat. We've saturated that particular network based on the configuration we had. We already know what the number should have been, and that's exactly what we got. Almost perfect. And you can see it's very flat and fairly stable. Now, what you can see in this context is something that looks like it'll go all over the place. And a lot of times that originates from the fact that the DTN, the data transfer node itself, is not properly configured. For example, if you had multiple cores on a DTN and you didn't configure your computer correctly, it may only be using one of the cores as opposed to all of the cores for the data movement. And so that causes some tension. And so by improving that, you could really make things better. Likewise, you might have some mistakes in your FTS setups. And so there's a lot of little things that could go wrong in terms of optimizing your network, your networking. And so having these data challenges allows you to ensure that, things are performing as expected. Typically, these data challenges are done before the actual experiments are going to run in order to kind of, gain confidence in the system, everything's working, communicate with the network provider. If there's a problem, you might do some disaster tests where you intentionally clip a certain side of the communication. So as an example, P&L had the Seattle and Boise connection. If you clip the Seattle connection, does everything work on the Boise side? So you can make these mock-ups and make sure that everything's working as one would expect. So once you have the resources in play, your network is working, your storage is there, your compute is there, everybody agrees to be part of this, you really need a tool that allows you to do this orchestration. And so in this context, I'm just going to show kind of an example of one that is called DIRAC. This is the one I've been using. So that, yes, there's a total bias here, and it's not the only one. So I'll openly say it's not the only one. But to me, it really is probably the best one in terms of a general full-featured package. And I'll kind of explain what I mean by full-featured. But a lot of these tools have been developed, of course, for the LHC. So DIRAC in particular was developed for LHCb. And so it provides a lot of tools to do this orchestration. So at the heart of it, large distributed computing without a scheduler doesn't really serve much purpose. So the first thing you would think about is the work management system. So that provides you the users to submit the user submission functionality. So at the heart of it, it hides the heterogeneous backend of all the computing and all the variations in the computing. For a user, they submit a job almost like if it was a Slurm submit or another cluster submission. Is really not the user does not see any of the, hey, is this an x86 or is this other architecture? It doesn't really matter to the user. They simply say, I have this executable. This is what I need to run. This is how much memory I need for it. I need this much storage for it, and they submit it, and it will go through the work management system. Equally important is the data management system, which again provides the functionality to upload, register local files to the storage, also register it into the catalog systems. It also enables this bulk data replication through the FTS server that we were talking about. And also allows you to pre-stage the tape systems so that if you needed something to be ran that was on tape, that you'd be able to access that tape drive as necessary. So it kind of stages things accordingly. And finally, the other thing that I find really useful is what's called the transformation system. And this is the automation functionality I was talking about earlier on. It really allows you to kind of plug and play various components in order to kind of have equivalent to a DAG where you could define a sequence of logics and it will work through those logics to define this workflow. So again, for me, DIRAC is really provided a nice solution that allows us to kind of have all of this in one integrated system. And a lot of times what you'll find in the LHC products is that you'll have somebody that's extremely good at the workflow management system or extremely good at the data management system, but very few, in fact, if any, I only know of DIRAC, will actually have it all integrated into one holistic package. So that's really a really nice feature to keep in mind. But nonetheless, there's a lot of ways you can do this, and by no means this is the only solution, but I'm just presenting this one as a solution. So I wanted to give a bit of an example of how some of this works in terms of what does a workflow look like in what does like an orchestration really would look like if I was a user and so forth. What are the components that we haven't really talked about and we really don't have time to talk about, or maybe we would, but nonetheless, this is kind of a very high level view about some of the key concepts that we haven't talked about yet. First of all, let's start with the illustration. You have a user or a prod. When I say prod, that's a production user. They're going to submit jobs to the work management system, right? So that's the arrows going into the work management system in the gray box. And you have a sandbox and a task queue. Now, the sandbox is a really interesting feature that is absolutely required. So whenever you have a job that you submit to a local resource, you never had to think, is that file that I have in my folder going to be available to execute? Of course it will, because it will see it. Well, when it comes to distributed computing, that file that is necessary to run my job is only on my local system. And unless I have a mechanism to share it to the rest of the compute resources, it will not be available. So that's what the sandbox is. What it does is it takes in input files that are required to run your jobs. But these are definitely not the same as physical files that are being stored in the storage systems, okay? So there's a distinction here. If you have to use a file that is part of a raw data file from some previous run, you could easily have access to this. That's an easy call. But if you need to add additional information, additional data into your job, that's where the sandbox comes in. Typically, users have restrictions and production users have different restrictions. There's a bit of rules here about how much space you can take, and you could coordinate this with your production manager. Once you have that, there's a task queue. This is really where all the tasks that are coming in from different places are being put into and essentially getting shuffled. Then we have the service matcher, or the this effectively receives requests from the pilot jobs and says, hey, you're this kind of hardware, I will give you this particular job. So again, what happens is this is a pull request. And let me step back a little bit and explain a bit about the pilot job. So what you see here on the bottom of the figure is this site director. This site director effectively submits what are called pilot jobs, okay? The pilot jobs are kind of like empty jobs initially that are only there to kind of assess the quality, the sanity of the resource. So it'll do all these, you could define a large script of sanity checks, like does it have memory, does it have storage, does it have the right OS, does it have XYZ? It captures all that information, and once it knows all that information, it goes to the matcher and says, hey, I'm a resource, I have this available. Is there a job that matches my definition? If there is, then the pilot job will pull down that payload into the compute resource and then execute. Okay, so you're always generating these pilot jobs that are really doing nothing apart from assessing, its environment and then communicating back to the DIRAC system. So that's the heart of how this pilot job and the work management system orchestration works. Is it's typically done by a pull request where the pilot jobs are just always asking, give me something to do, this is what I am, okay? So then on another example I want to share is how you do automation. So again, for my previous work, I've used DIRAC, so I'm going to use DIRAC as my example here. And what DIRAC has is this like a complete solution. And it has this automation feature that allows us to kind of get a lot of work done with very little human resources. And that to me is really critical for smaller experiments. So it's fine if you have 20 FTEs at CERN to do some of this monitoring and some manual job submissions and so forth. It's a lot harder when you have a very small group of people. So one of the projects I was on that I was leading the computing effort was modest size project. That definitely didn't have, an army of postdocs or grad students to man the compute workflows. So what we developed was this extension of the transformation system, where essentially whenever a raw file, so as you're going through the figures at the bottom, you have a raw file, it gets registered into your data catalog, it gets associated some metadata. So metadata being what is the file type, what is the run type, all these kind of metadata you might have. And based on that, that would trigger a processing workflow that would go from process the data, merge the data, analyze the data, and then give me some results. And so this would be a full automatic stream, and you could add as many steps to this as you would want. But it was always triggered by when data was being generated as opposed to just submitting jobs manually. So whenever something showed up in the catalog, because we had defined the metadata, we were able to trigger this immediately to move things across and just transfer the data as required. So again, that's just a really, to me, a really automation in large scale computing is always a major plus, and it's not always something that you have available. So this is something I thought was I wanted to share. So,
sorry, Malachi,
yeah.
Sorry. We are almost 50 minutes. So
I'm at my last slide. Perfect.
Oh, perfect. Thank you.
I timed it right. All right. So last slide. So I
Perfect. Thank you.
Absolutely. So I wanted to just bring up a bit of a side note on designing a flexible infrastructure. This is just some experience, and this is partly to just share with students or some of our lessons learned. One of the things that we've gone ahead and done is pretty well all core services at the sites that I've been involved with have all converted to using something like Kubernetes to kind of manage the containers. That allows us to now have break down all the service layers and provide instances for service A, X, Y, Z, agents and databases. So everything's kind of a containerized representation. And if you needed more horsepower on a database or a service, you could add an extra container and you could orchestrate it correctly. So for us, this was really critical. And it was also critical for us to be able to do that because of the DevOps workflow. So as you're developing these development products, you want to be able to kind of test them very quickly. And then if they work, you could just easily switch them over into your production system and out. Again, Kubernetes allowed us to do this pretty easily. It also gave us maximal flexibility to work with your collaborators. So as I was mentioning earlier on, some of the problems that we've had in the past was always the OSs, when we had multiple projects on a cluster, which is pretty common. Now, the second you allow people to have containers, what that enables you to do is say, hey, you figure out what you want, put in that container, compile it yourself, and then when your bit are ready, we'll convert it to a singularity image, and that singularity image will put it onto the HPC system for us to execute, and we'll link it into the actual job submission queue. And the reason why that's really nice is because in the past, whenever somebody would give us, hey, this is something we want to put into stratum 0, the problem was always going to be something alike. The person only tested it on this particular system, which was not quite our system. And there was always little nuances like that we always end up losing time trying to figure out why did it work here and not there. And again, with a container, you just always updated the container. It was always a much easier system to build on. So anyways, that's, as a side note, one of the things that worked very, very nicely for us is really going towards that fully virtualized, containerized environment for our, not only our infrastructure, but also our compute resources. And then with that, I'll just finish up with, please be aware that there's other talks coming up that are for computing. and data science. So Graham will be presenting tomorrow, and so will I. And I hopefully we'll see you tomorrow and discuss some more interesting computing and data science topics. With that, I'll stop and take questions.
Okay. Thank you very much, Malachi, for the really nice overview about distributing computer. It's very interesting. So just raise your hand. Don't be shy. So if there are no questions, I would like actually to
Alex,
ask.
there is a question
Sorry, I didn't see it.
from Gabriel Rodriguez Linera.
Go ahead, Juan. Ask it.
Hi. Thanks. So one, like a theme I feel like I've gotten through today's talk and yesterday's talk on like these computing topics and nuclear physics is that I feel like a lot of this like the type of knowledge that is being implemented is not the usual like physics type of thinking or knowledge or things that we're just really thinking about, but it's a lot more like what industry, like private industries, tend to be thinking about, like how to manage things without the user having to do them themselves and stuff like this. So I guess my question is, do you guys like collaborate with private industries and stuff like, for example?
So again, I've only been at JLab for a month, but definitely at P&L, we did have conversations with Google, Amazon, etc. In order to identify places of collaboration, for sure. Things that are relevant to them are they have their cloud system, and so I think I showed that in one of the figures where we definitely use clouds for when necessary. It's not we've done some cost analysis. It's not yet clear how beneficial or cost effective it is to use clouds, but definitely identifying paths to collaborate with industry is important. Another thing I'd say is that at least with the work that I've done at P&L prior to JLab, our focus has definitely been to try to identify the trends that are happening within industry that is enabling these kind of workflows. So for example, Kubernetes, we've been doing this for years and years and years, and containers. One of the reasons was to be able to attract talent that would like to work with us, but may be apprehensive a little bit because some of the software stacks that we've been using are very niche in terms of high energy physics and nuclear physics. And so when you actually generalize the software stacks and there's a usability outside of this particular work, I think that makes it much more attractive for computer scientists, because now there's like a life outside of XYZ. And as much as we never want to see them leave, it's something that's important to be able to develop a workforce that is very flexible in their abilities to address problems across various topics. And by using industry standards, that definitely enables them to do that.
Thank you.
There is another raised hand from Patricia.
Yes, thank you. Thank you so much for your talk. My question is more oriented to my current PhD project, because I would like to know which of these computing tools that you have been talking about would be more useful for high energy physics of work, and in particular phenomenology, because you have mentioned Docker, for instance, but I'm not really sure what Docker is about, and I don't know if you have mentioned during this talk any tool that could be more that could be applied in this area that I'm talking about. Thank you.
I think I would need to understand. I would need to understand a little bit more what exactly you're doing and how you currently plan to do it. So feel free if you want. I don't know if it's a conversation we need to have. Oh,
Yeah,
go ahead.
I didn't mean like specifically in my project. I meant more in like high energy physics software and projects connected to phenomenology. Like for example, you mentioned Monte Carlo event generators and things like that. Like we usually only focus on a specific type of software that we work with, but then I think these tools that you are mentioned maybe could have an application regarding making things easier, like making the computational work or a bit more practical, like more like for example, sometimes it can happen that different teams work with different softwares, or I don't know, like it was more a general question about how to apply the knowledge that you have given in today's talk to our area.
Sure. Maybe I'll give you an example. I don't know if I'll answer the question, or at least maybe I'll give. So when it comes to containers, what you're really doing here is enabling transport, the ability to transport your software stack to different hardware configurations. As an example, for machine learning, something that I've done in the past was we created a container that would actually capture all the data science tools that one would want to use for a student or grad student or postdoc or myself. So we had a common container that we'd all use. And because it's a container, we could just run it initially for prototyping on our laptops. Afterwards, we could actually, with some very minimal configure changes, if any, we could then move that to an HPC system. So it was fairly easy to go from laptop prototyping to production distribution to, on an HPC system. So in that context, containers are really good for that, I find. But you have to realize that there's some limitations in the containers. If, for example, you're submitting a job on a specific GPU, then those components that are necessary for the GPU need to be embedded, and that has to be done correctly. So there's an added complexity there. It's a container, like a container has to also still be cognizant of its environment to some extent. Although we say it doesn't, it does for some of this.
Okay, thank you.
Yeah.
We have another raised hand from Ching Him Leung. Sorry if I mispronounced. Go ahead.
Yep, you pronounced it correctly. So what are the common problems you see users made when doing grid computing?
Common problems. That's, well, I'm trying to think about the problems that we've had at our sites.
Or a mistake that user made when
users. Well, okay, so I think one of the common problems is communication. And I know that sounds like a very generic statement, but the expectations of the collaboration and how they're going to use your tools is a common problem that I find. No matter what collaboration you're part of, it takes a while for them to understand exactly what we meant by this type of distributed computing. So a common problem for users are sometimes they will submit jobs that are very IO intensive because they might have had really bad code. So if it's and so that has impact on the sites. As a very clear example, I mean, we've had problems where jobs were submitted where it was just completely hammering the IO. And because some of the sites have shared storage, one would then have the whole system, because it's a shared Lustre file system, be impacted by this, and the overall performance of the site itself gets clobbered. So I think that's a very clear problem. One of the things that I've worked on in the past is trying to identify when we could actually model those problems coming forward and then actually mitigate the problem. So if we realize that some workflows are very IO intensive, then we need to schedule those jobs accordingly and mitigate that risk. So that's definitely a problem that we see a lot, and that's originating from software development experience that they need to understand how to use the system a bit better. But that's true of local computing too, but it's definitely amplified on the grid side. I hope that answers at least that. So that's an example. How's that?
Thank you. Yeah. I think the software that we had in my experiment definitely fall into the IO intensive part. So
yeah,
Okay.
and I would say that the orchestrations that are available typically are focused on CPU and do not really consider a lot of the other elements of the workflow like IO. And so that's definitely a place that can be improved. They've done it. The distributed computing as a whole is a remarkable effort, but there's always room to improve, and that's definitely a place that we've identified that could benefit from some improvements.
thank you.
Okay. We are taking the last question for this session. That is Shuja, I think. Sorry if I misunderstand the pronunciation. And then I recommend you, if you have other questions, to use our Slack channel again to ask questions to Malakai. So please, Shuja.
Yeah, thank you. I'm just curiosity that if we submit jobs on GLab RFM, are we going to use like nodes outside GLab, or like it depends on, you are talking about the Japan Bell 2 experiment, or it depends on like which experiment, which collaboration are you working on?
Exactly. So what happens is when you create an instance of DIRAC, for example, you need to define the resources that are going to be orchestrated. So there's a section called the configuration section, at which point you say, okay, I'm going to create storage element A, B, and C, and they will be at site, Brookhaven, JLab, and let's say Argonne. So every DIRAC instance will have or configuration defining exactly which resources it will use. So if you, for example, if DIRAC becomes something that we have at JLab, you would actually be able to actually see what resources are there, but you wouldn't have to really think about what's being used. It would just submit the job accordingly to what resources are matches the requirements of your job, and also that is available.
GLab is not part of it yet.
Pardon me?
So GLab is not part of DIRAC yet.
Not yet.
Okay.
Okay, so let's thank Malakai again, and he will be our lecturer also for other 3 lectures. So thank you very much, and we will see you in about 20 minutes, 11:25 a.m. Thank you again, Malakai.
Thank you.
slide looks good.
Thank you. Can you also hear me? Hello, everyone.
Yep, I can hear you.
Okay, very good. So, I mean, whenever you guys, we can still wait till 5 minutes. I was just checking. Let me also switch on my camera. You can, yep.
Awesome. Yep, we can hear you. We can see you.
Okay, very good. So, whenever you guys want to, we can start.
So Juan, I think we'll wait for Alex. Does that sound good?
Yes. Let me see. Yeah, we can wait maybe a couple of
Juan, you are chair now,
Yeah.
right?
Yeah.
Yeah, Filippo is coming.
Okay, that's good. Hello, Carlos. How are you?
Hello, very good. How are you doing?
Not too bad. Thank you for joining us and for the lectures. We're very happy to see them. If you can switch on your camera while you talk, it would be great. I think it adds a dimension to the.
I can try. I mean, you let me know if there's some connection issues.
Yeah. So
sometimes it's a little bit, you know.
Okay. But if it works, it's great for the students to see the face and expression.
No, I agree, and it would be nice also to see the students. I mean, but
so what we ask them, actually, Juan, you may remind me, what we ask them is to switch on their camera when they ask questions. So
yeah, okay, that's already helpful. Yes.
And so I hope that it produces at least a little bit of what we're used to in the class, in the seminar room.
Yeah, it's not the same, but you know, that's the best we can do these days.
Not too bad. The more I get used to it, I think a hybrid sort of system going forward might be good. We can take advantage of it.
Let me see if I'm trying to, let me unshare 1 second.
Yeah, sure. Yeah, I think Carlos, Juan, we will be chairing the session in general, coordinating the times and everything. And I think Filippo will monitor for questions in chat and other things like this. So,
okay, so that's very good. So what I was gonna say, I mean, people should can interrupt me during the presentation, even if there's a question session at the end. I mean,
yes,
I will not be able probably to see the hands up and so on, but you guys tell me.
Exactly. So you focus on the lecture and we interrupt you, and then
exactly.
you can have a discussion with the students.
Hi, Carlos. Nice to meet you.
Hello. How are you?
Good.
Let me get this ready. So you should see the screen again, I think.
Yes, we do.
Let's see. Okay.
Sorry, Filippo is not able to connect because he has some problem with the Wi-Fi. You can go on if you want.
Okay, are we starting now? Perfect. So
I think is better, yes.
So hello everyone again. Welcome back to eHawks 2021. My name is Juan Guerrero and I will be your session chair today together with Alex and Alberto that will be around. Just as a quick reminder, eHawks students feel free to ask questions at any time. You can raise your hand and we can interrupt the speaker and bring the questions. All other attendees can write your questions in the Q&A tab, and any of us will collect the answers and we will bring them by the end of the session to the speaker. Today's speaker is Dr. Carlos Muñoz Camacho. He's a researcher at REYES. He's an experimental physicist working in 3D special structure of nucleus and nuclei, and actually is the topic of the lecture. So welcome, Carlos, and you can start.
Thank you very much. So good morning, everyone. So thank you for the introduction. That's basically what I was gonna say. So as I'm an experimentalist who have been working at JLab for about the last 15 years, and particularly in experiments related to deeply virtual quantum scattering. So which is the topic we'll be covering during these lectures. So let's get started. So we will have 5 lectures together. So here's an outline of the topics I'm planning to cover in each of them. So today we will mostly an introduction to the overall topic. So I'll start discussing elastic scattering and the observables that we measure with that, which are they are called form factors. Then I will go on to describe what we usually call deep inelastic scattering and the observables, which are the Parton distribution functions or PDFs. And finally, we'll discuss the so-called exclusive reactions and generalization of there are generalization of PDFs referred as generalized Parton distributions. Then tomorrow we'll discuss deeply virtual quantum scattering in more detail, so with an overview of some experimental results using both protons and quasi-free neutron targets. That would be lecture number 2, and then later in lecture number 3, again, still tomorrow, we will cover a complementary channel to access GPDs, which is the electron production of mesons in the deep virtual limit. So this is a particularly interesting channel to access the so-called transversity GPDs of the neutron. And we'll, of course, describe what those are. And then the last day on Friday, lecture 4, we'll have a quick overview of the theoretical models and parametrizations of GPDs, and then give an outlook of future experiments planned at JLab to study GPDs. And if we manage to cover that in these 4 lectures, then the final lecture will be dedicated to the imaging of gluons in the nucleon, and we will describe in some detail the project of a future electron-ion collider, which is currently in preparation, and among other topics, it will provide a way to access the 3-dimensional structure of nucleons and nuclei at low X, where they are mainly dominated by their gluon content. So I didn't see a dedicated lecture or topic on EAC. That's why I wanted to include that at least a little bit on my lectures at the end. So let's get started. So today will be, as I said, an introduction. We'll start describing elastic scattering, then deep inelastic scattering, where I will introduce the very important concept of factorization, which of course was already discussed by Yang Wei yesterday, but I will explain a little bit how it applies specifically to the case of DIS and then of exclusive reactions. And then the last part of the lecture will introduce so-called off-forward Compton scattering as a generalization of the deep inelastic scattering, and then generalized Parton distributions as a generalization of PDFs. And an interesting twist of the DVCS reaction is its interference with the so-called beta-hydride process, and we will describe the implications of that for the measurements of GPDs. So now the mother of all scattering experiments is really the one performed by Rutherford in the early 1900s. So it was really the first exploration of subatomic structure. And it was done by bombarding a foil of gold using alpha particles. And the technique is actually very similar to what we still do nowadays. So at the time, the model of the atom was defined basically by electrons surrounded by a volume of positive charge, like negatively charged plums embedded in a positive charge pudding, and that's how the name came of a plum pudding model. So in this model, one expects particle to deviate very slightly when going through the gold foil. Now, what instead was observed was that alpha particles scatter at significant large angles, which was more consistent with a positive charge concentrated in a very small volume. Now, the number of particles deflected by a given angle at a given angle was indeed compatible with all the positive charge concentrated into a single point, which is now called the nucleus of the atom. And the experiments we will be discussing in these lectures, we will use higher energy particles than alpha particles. We'll be able to resolve the structure of the nucleus, but the experimental technique actually is almost identical. We will measure the number of particles scattered at an angle to tell us about the structure of the target. And we will measure the cross-section for a given reaction as a function of different variables: the scattering angle, the energy of the beam, the energy of the scattered particle, and so on. But really, not very different from what was done by Rutherford more than a century ago. So let's start with the most simple process to probe the structure of the nucleon, structure of protons or neutrons, which is elastic scattering. So the use, for example, of an electron beam, which interacts with the target using a virtual and there is a momentum transfer between the electron and the target, which corresponds to the virtuality of the exchange photon. Then what we do is to measure the cross section as a function of this momentum transfer Q, and compare it to the one that one can calculate assuming a point like scattering. So that is when all the charge is concentrated in a single point. Now, if we forget about spin for a second, so the interpretation is very simple, and the deviation of this cross section compared with respect to the point like cross section can be directly related to the Fourier transform of the charge distribution of the target. And we call that deviation from a point like structure the form factor of the target. Now, things get slightly more complicated when one introduces spin, but the principle remains the same, right? In case of spin 1/2 particles, which is of course the case of the nucleon, there are actually two form factors that one can define. They're usually referred to as electric form factor and magnetic form factors. So GE and GM. And the deviation of the measured cross-section with respect to the point like calculation, that is called sigma mod or mod cross-section, can be parameterized in this form, where GE and GM are the two form factors of the proton. Now you have one observable, the cross-section, and two unknowns, the two form factors. So in order to determine to determine both form factors independently, one needs to play with a little bit with the kinematics. And you see, for example, here that this equation depends on the initial electron energy. So therefore, but by measuring the cross section at two different beam energies, for example, and keeping all the other variables constant, one can independently measure each of the two form factors. This is a technique that is usually called a Rosenbluth separation of the cross section or form factors. So these quantities have been measured for many years now and in many different experiments in a wide range of momentum transfer Q squared. And these plots summarize most of the experimental data available, not all of it, but most of it. For each of these two form factors, the electric form factor on the left and the magnetic form factor on the right, with each color corresponding to different experiments. We'll not go into the details, it's not the point here, but what you will notice is that the plot for the form factor is divided by this GD, so this is called the dipole form factor, which has this expression here, and it turns out to describe the Q-square dependence of the measured form factor reasonably well. So we usually plot the deviations with respect to this dipole form factor. And you see that the electric form factor, these deviations are very small, even through the full Q-square range. There is a little bit more important deviations in the magnetic form factor. But the dipole form factor basically has the functional shape illustrated in this schematic figure. So it decreases with Q square, which is the size of the proton that the visual photon sees. So when you increase your resolution, the value of Q square, the virtual photon sees less size of the proton, and so it sees less charge. So that's why basically the form factor decreases. So that makes sense. On the other hand, a point-like particle will give a form factor which is independent of Q square, which is what that would mean that the virtual photon will always see all the charge independently of the value of Q square. So then one can Fourier transfer these quantities, as I said at the beginning, to create two-dimensional images of the transverse distribution of charge inside the nucleon. And you can see here these two images, on the left for the proton, on the right for the neutron. And particularly interesting, for example, is the fact that for the neutron, we observe a core of negative charge surrounded by a positive outer surface. So this is the most straightforward, I would say, spatial imaging of the nucleon internal structure one can do. So based on the elastic form factors and elastic scattering and elastic form factor measurements. Now, I'll move to a different process we can look at to study the internal structure of the nucleon, which is the deep inelastic scattering. So here we also use an electron beam, usually that changes a virtual photon with the target. But now the proton is typically broken apart, and experimentally we only measure the scattered electron. So basically we integrate all over all possible final states of the hadronic system. And again, for one spin 1/2 particles, the cross section can be written as a function of two quantities, which are called structure functions, W1 and W2. That parameterize the cross section with respect, again, to the point-like Mott cross section. Now, when this was first measured in SLAC in the 60s, it was very surprising to observe that the ratio of the cross-section with respect to the point like mod cross-section had no Q-square dependence. So as I said at the beginning, this is an indication, not at the beginning, a couple of slides ago, this is an indication that we're indeed scattering of a point-like particles. So the virtual photon sees all the charge independently of the value of Q square. So these point-like particles is what we now call the quarks. So it was observed that the structure functions that could be in principle depend on two variables, the energy of the virtual photon and its mass, Q square, and nu, did only depend on one parameter, actually. So it's a property that is known is known as Born scaling. Now, to interpret these results, so again, at the time where the concept of quarks, as we know it today, did not exist yet. So Richard Feynman came with the so-called Barton model. So in this model, the proton is basically composed of point-like partons, from which the electron scatters. Excuse me. And in an infinite momentum frame of reference, then time is dilated and it slows down the motion of the constituents inside the nucleus. So partons are assumed not to interact with each other, with one another, while the virtual photon is exchanged. So it's what we call today the impulse approximation. So in this model, the electron scatters from constituents that are free, basically, and therefore the scattering gives us information about the motion of those constituents, right? So indeed, the parton distribution functions that we measure in deep inelastic scattering can be interpreted as the probability, as the momentum distribution of partons inside the nucleus. So it's also interesting to note that this near vanishing parton-parton interaction, assumed in the parton model during the scattering, was later shown to be a consequence of QCD, it's the property of QCD known as asymptotic freedom. So the parton model allows one to introduce the concept of factorization, and that's why I wanted to talk about it here, because it's a concept which is a cornerstone in QCD calculations, but in particular for the topic of these lectures. So in the parton model, since partons don't interact among themselves while the virtual photon is exchanged, so the cross-section, deep inelastic DIS cross-section, can be written as the product of the partonic cross-section, so the electron-parton cross-section, times the probability, basically, of probability function of the parton that carries a given momentum fraction. So it's the product of the electron-parton cross-section as a function of a given momentum fraction of the parton times the probability of that parton carrying that momentum fraction. So it's really a product of two different quantities. Now the first one, so, well, and then just the sum runs over the different flavors of partons. That's not really important here. This is really the concept of factorization. The cross-section can be written as the product of a quantity that we can calculate perturbatively. So this is the point-like cross-section. So the photon, the electron quark cross-section, so two point-like particles, we can calculate in perturbative QCD. And then some function that we cannot calculate perturbatively that parameterizes the structure of the target, in this case, the momentum distribution of the partons, and which is a function which is universal, and it appears in many other different processes. So in the form of Feynman diagrams, we usually know the scattering of a single parton this way. So the upper part of the diagram shows the electron quark interaction, which is perturbative, and then the lower part, which is parameterized in this case by this parton distribution function. And then using the optical theorem, we can relate the deep inelastic scattering cross-section to the imaginary part of the so-called forward Compton amplitude, where both the initial and the final part on here carries the same momentum fraction, which in the case of DIS turns out to be the ratio of Q squared divided by 2 times the product of the proton and virtual photon momentum. And we usually refer to this quantity as X working. Now, a generalization of this forward Compton scattering diagram is the so-called off-forward. Of forward Compton scattering, where the momentum fraction of the initial state parton is different from the momentum fraction of the final state parton. And we can achieve that experimentally, for example, by going from a virtual photon in the initial state to a real photon in the final state, which is the case of this process, usually known as deeply virtual Compton scattering, or DVCS. Where you see here basically the lowest order diagram. So a highly virtual photon basically interacts with a single quark of the nucleon, which carries a momentum fraction X plus psi. It absorbs this photon, and then it emits a high energy real photon, which makes its momentum fraction different in the final state. So X minus psi, but the target, the nucleon, remains intact. So there is an overall momentum transfer to the target T, which is defined as the difference of momenta squared between the initial and the final proton. But this momentum transfer is different than the value of Q squared, which is in this case is related to the virtuality of the virtual photon. So in the case of elastic scattering, T and Q squared coincide. Here we have 2 different variables: momentum transfer of the virtual photon and the one on the proton. So indeed, if Q squared is sufficiently large, the amplitude of the process can be factorized into components, similar to what I just described for the DIS. A hard perturbative part, the interaction of the photon with the quark, and a soft non-perturbative part, which describes the internal structure of the target. and we parameterize this internal structure now by the set of functions known as generalized parton distributions or GPDs. So they depend on 3 variables. As you can see here, the average momentum fraction of the quark, X, the variable psi, which is related to the longitudinal momentum transfer, to the difference between the momentum fraction in the initial and the final state. And finally, the variable T, as I said, which is the overall momentum transfer to the proton. So this is the reaction we will be dealing with for the remaining of this lecture, and especially during lecture 2 tomorrow. So you notice that there are 4 GPDs defined here, labeled H, E, H tilde, and E tilde. Now this number of 4 is related to the different combinations of quark and nucleon helicities. So we refer.
Carlos?
Yeah.
Hi, could I ask a quick question?
Of
on
course,
the previous
yes.
slide? Okay, let me lower my hand. So on the previous slide, when you were showing this handbag mechanism kind of diagram, where there's only one quark that this virtual photon is interacting with. I was wondering if there are any assumptions on what happens to the rest of the nucleon, which are spectator in quotes, that keeps it intact. I mean, there must still be interacting with this one quark to hold it back, right? Are there any assumptions that are going into this interaction?
Well, the assumptions is a little bit what I was describing before, right? So we assume that there is no interaction between the other partons and between the parton that interact. So everything, all partons are free, so to speak. So that's the lowest order diagram, of course. This is what we call the leading disk diagram. There are corrections and higher orders where you have several partons and partons interacting with one another. But the assumption of this diagram is yes, that the other partons are just spectators. So there's only one interacting with the virtual photon. I don't know if that answers your question, or it was
yes.
different.
Yes. Thank you.
So then, I was saying why there are 4 GPDs, and I mean there are actually 8, but there are 4 because again it's related to the spin of the quark and the nucleon, so it's related to the different combinations of quark and nucleon helicities. Sorry, 1 second here. My computer is. Sorry. So we refer to these 4 GPDs as the chiral even GPDs because the helicity of the quark is conserved. So as I note here by the plus and minus the sign, the helicities of the quark and the nucleon. So all these GPDs are described here. They conserve the helicity of the quark. But depending on the different label, they will flip the helicity of the nucleon. So H and H tilde will conserve the helicity of the nucleon, whereas E and E tilde will flip the helicity of the nucleon. Then you can combine them with plus or minus. Now there are indeed 4 other GPDs referred to as chiral odd GPDs or transversity GPDs that flip the helicity of the quarks. They do not enter in the DVCS process, so that's why I don't describe them here today, but they will be discussed briefly in lecture 3 when we will be dealing with deeply virtual meson production. Now, so GPDs are mostly unknown quantities, but they must observe a number of constraints. So as a generalization of parton distribution functions, they should coincide with PDFs in the limit of t equals 0 and xi equals 0. That's a first constraint. Also, their first moments are related to the form factors. So the integrals over x are related to the form factors. That gives another constraint. Now, a very constraining property is this one called polynomiality, which states actually that the moment of order n of a GPD must be a polynomial in psi of order n. And this is a very important constraint, and it's not so easy to implement when one wants to model GPDs. So we will come back to this during lecture 4, when we will describe theoretical models, but that's a very important and interesting mathematical relation that GPDs must observe. Maybe the most interesting property of GPDs, which was basically the one which attracted all the attention to them and really started this field of research, is the so-called G's sum rule, that basically states that the second moment of the sum of GPDs H and E is related to the contribution of the angular momentum of quarks or gluons to the nucleon spin. So many of you might have heard of about the so-called proton spin crisis, which was based on the measurement of the contribution of the spin of quarks to the total spin on the nucleon, and it was found to be small. Now there are ways to access experimentally the contribution of quarks to the nucleon spin of gluons, but the contribution coming from orbital angular momentum is much more complex to measure experimentally. And up to now, this sum rule is really the only hope to measure this quantity. Of course, it is still not easy, since one would need to have a good knowledge of these two GPDs, H and E, over the full domain in X, because it's an integral in X. And you will also need to take the limit of t equals 0, which is, of course, something you cannot measure experimentally. So you will need some kind of extrapolation to do that. But still, if with sufficiently amount of data, with some control over this extrapolation and the integration of the full range in X, this sum rule is a very interesting quantity that strongly motivates all these measurements of DVCS and GPDs in general. Now, GPDs are functions that depend on three variables, and of course, it's not easy to give an easy physical interpretation. But now, Matthias Burkett and Marcus Deal came up with a kind of intuitive interpretation of what GPDs mean in the transverse plane of the nucleon. So the variable t is the Fourier transform of the so-called impact parameter. So basically, it gives the position in the transverse plane where the initial quark is located. Then the variable psi determines actually the transverse shift. So between the proton, between the initial and the final state. And then X, that's a little bit easier. It's just the average momentum fraction of the quark involved. So this is why we typically refer to GPDs as three-dimensional imaging of the nucleon. So it's basically a two-dimensional space imaging in the transverse plane, plus the longitudinal momentum of protons. So it's more like a 2+1 imaging of the internal structure of protons and neutrons. So this is typically the kind of images one would be able to do with GPDs. So it's something similar to what I showed with form factors before, but now as a function of the momentum transfer as an additional dimension. So for example, the figure on the left shows the distribution of quark U at low momentum fraction in the top, and with increasing momentum fraction from top to bottom. And we see that the quarks with high momentum fraction are localized in a much smaller region than those at the lower momentum fraction, for example. And we can do that also for a polarized proton, the second column here, where the distributions are no longer symmetric due to the polarization of the proton. And finally, the right figure, you see the equivalent distribution, but for a quark D. Of course, at this point, this is all based on a model of GPD. So the goal of the experimental program is obviously to try to make these kind of images based on experimental data. Now, one interesting feature of DVCS is the interference with the so-called beta Heidler process. So where the real photon of the final state is not emitted by the proton, but by the electron, either the initial or the final scattered electron. So now you see that this process has the same initial and final state. So it interferes with DVCS at the amplitude level. So this is a very interesting thing, though, because actually the beta Heidler amplitude can be calculated in QED. So if we know the form factors of the nucleon. The vertex here is a QED vertex that we can calculate analytically, basically. So in practice, we have an interference of a process, DVCS, with one which whose amplitude we can calculate. So this allows to make one kind of analogy to what we do in holography, where we are able to reconstruct the three-dimensional image of an object from the interference pattern of beam reflected from the object and then a reference beam, right? Something similar, of course, this is just an analogy, so one should not push it too much, but something similar is happening with DVCS and the Bethe-Heitler process, right? One would detect the experimental data, the interference pattern of DVCS amplitude and the Bethe-Heitler amplitude, which allows not only to measure the amplitude squared, which is the cross-section, DVCS cross-section, but also its phase with respect to the Bethe-Heitler amplitude. So, which in fact contains much more information, of course, than the amplitude squared, which is usually what we measure. When we measure a cross-section, you only measure the amplitude squared. Now we can access through the interference of DVCS and Bethe-Heitler the real the amplitude of the DVCS process at the amplitude level.
Carlos, excuse me, there is a raised hand. Aaron, go ahead.
Hi, Carlos. One more question on your previous slide. Actually,
this one here or previous one?
Previous one. It's actually 20.
20. Oh.
Yeah. So 20. Yeah. Okay. So if I understand this correctly, the interpretation or the 2D transverse position interpretation is that the proton shifts from its initially scattered position to acquire some transverse momentum, and that is interpreted as the transverse position of the quark that got scattered inside this proton. Am I right?
Yes, that's the interpretation of this variable psi. Yes.
Psi. Okay. And so I'm thinking or trying to connect the picture from a few slides ago where only one quark interacts with this virtual photon, gets pulled back because the nucleon has to be intact, and this transverse momentum gets redistributed among quarks and gluons. And how do we the reconstructed transverse position is smeared out, right, amongst the proton. So how is it extracted back to the transverse position of just one quark?
Well, let's see. I'm not sure I fully understand the question, but so there's no interaction as we discussed before between the spectators, right? In this handbag diagram, right. So everything happens with one quark. So it gets one momentum at the beginning, and because of the absorption of the virtual photon and the emission of a real photon, then its momentum fraction changes. All the other ones are supposed to be, all the other partons are not changing their momentum fraction.
Right.
Now, so what was,
so
can you repeat the question? I mean,
sure.
I'm not sure I understood. Yeah.
Sure. I guess what I'm trying to get an intuition for is after this quark emits a high energy photon, right? It comes back into the proton or merges with its spectators, right? Now the proton is intact. What we observe with our detectors is this proton, right? And so we're looking at the transverse shift of the proton itself from its initial collision. So I guess, how do we separate out the transverse position that is acquired because the rest of the proton interacts with this quark that emitted out?
Okay, maybe I understand. Let me rephrase it to see if I understand your question. Your question is, how do we measure this shift experimentally? Is that what you mean, this shift of the proton?
Right. How do we measure it experimentally and connect it back to the quark's transverse position? Okay.
So the question is that that's not what we measure, right? So what we measure is just a proton at a given angle. Now, it's the information about the photon mostly that give us information, right, about this, because the energy and the angle of emission of this photon, we can then trace it back to the position of the. So it's the kinematics of both the scatter electron and the emitted photon that can then be traced back to the actual momentum fraction of the quark. But you're right, the proton, you cannot measure that shift.
I see. Okay. Yeah. Thank you for answering the question.
Yeah. So it's the kinematics of you measure the kinematics actually of the three particles, and that you can trace it back later to the kinematics of the part at the parton level.
Right. Okay. Thank you.
So let's see. I think let me go back. Slide 23. So yes, so this is what I was explaining before in a little bit more mathematical way, right? Not the analogy anymore. So the photon electron production cross-section basically can be written as the sum of the beta-Heitler cross-section, again, which is well known, the DVCS cross-section plus the interference term. Now this interference term is complex, so it has a real and imaginary part, and we can actually access them independently by using, for example, a polarization, a polarized electron beam. So, for example, if one measures the cross-section difference with opposite beam helicities, one accesses the imaginary part of the interference term, whereas if one measures the unpolarized cross-section, one can be sensitive to the real part of the interference term. And so the real part of the interference amplitude, of the DVCS amplitude, sorry. Now, the interest of measuring these terms independently is that they contain different information on GPDs. So for example, the interference term will be a linear combination of GPDs, whereas they will appear squared in the DVCS square term, or in other words, DVCS square term will contain bilinear combinations of GPDs. So the DVCS reaction itself has a very rich structure as a function of the angle between the leptonic and hadronic plane. So let me describe a little bit here, because this angle will come a lot in the future in this lecture. So the leptonic plane is the reaction, is the one containing the initial and scatter electrons in the reaction, and the hadronic plane is the one containing the recoil and the recoil proton and the real photon. Now the angle between these two planes, usually we call it phi, and it's a very important kinematic variable because the cross section has a strong dependence on that angle that can actually be exploited in order to separate to a certain degree different contributions of the cross section. So you can see here the generic expression of the DVCS cross section, which has an azimuthal form in terms of cos phi and sinus phi, up to the order 3 in the interference term, and up to the order of 2 in the beta-Heitler and DVCS square term. So this is not a Fourier decomposition with an infinite number of terms. It's a limited number of terms, but you see that there are many different terms, which is in a way a good thing, because each of these terms in front of them has a different coefficient here, different amplitude, and each of them are related to a different combination of GPDs. So it will be a linear combination for the terms that are in front of the interference azimuthal terms, and there will be bilinear combinations of GPDs in the terms that appear in the DVC square terms, azimuthal decomposition. And of course, the beta hydra, as I said, it has the same dependence, but it's something, it doesn't depend on GPDs, it just depends on form factors, which are to a certain degree well known, and so we can basically subtract this term from the experimental data and just look at the interference plus the DVC square term in order to extract the GPD measurements we are interested in. So I will end up a little bit this lecture pointing out that ultimately GPDs are not an experimental observable themselves. So the real quantities that enter the DVCS cross-section are GPD integrals over the variable x. These are complex integrals, so of this type, where there is a real part which is related to the principal value integral shown here, and that can be accessed through unpolarized cross-section measurements. And then the imaginary part, we can measure with with a polarized beam, that it's the GPD itself, but along one particular kinematic line, x equals I. And it is what's illustrated here in this figure. Experimentally with DVCS, we can either access integrals along x or single points of GPDs, but along the diagonal x equal xi, or x equal minus xi to be precise. So it should be a plus minus here. So this, together with the fact that there are various GPDs and a large kinematic range to explore, it makes, of course, the experimental program very ambitious. So one of the goals, so in addition to exploit the phi dependence of the cross section, is to play with the different combinations of polarization of the beam and the target. So each observable is sensitive to a different combination of GPDs. For example, with a polarized beam and unpolarized target, we are sensitive to these combinations of combination of GPDs, so H, H tilde, and E, with a given kinematic factor in front of each of them. This particular observable, when you plug in the numbers, you will see that it's mostly dominated by GPD H, because for the proton, for example, F1 is much larger than F2. F1 and F2 are the form factors. For example, with a polarized beam and unpolarized target, again, the opposite, unpolarized beam and longitudinally polarized target, we are going to be sensitive to this other combination of GPDs, so slightly different, with slightly different weights in front of them. And again, when you plug in numbers, you will see that it's mostly sensitive to H tilde, so and so on and so forth. So you can play with as many degrees of freedom that you have, basically. Transverse longitudinal polarization of both beams and targets, in addition to the angle phi that I described in. So it's that basically gives idea of the many different kind of experiments that one needs to do in order to fully address the experimental program of GPDs. So in the next lecture, so I will be describing a little bit some of the results of this experimental program. So let me just maybe summarize the first lecture. So we described first the elastic form factors that provide a special imaging of the charge and magnetization of the proton and neutrons inside the transverse plane. So this is kind of a 2D. It's also 1D because it's just distance with respect to the center. So spatial imaging in one dimension. Then DIS and parton distribution functions, which provide a one-dimensional imaging of the longitudinal momentum of partons inside the nucleon. And now GPDs that provide a combination of both. So they allow kind of a 2+1 dimensional imaging of quarks and gluons, where the 2-dimensional is position in the transverse plane as a function of 1 dimension, the longitudinal momentum of partons. So GPDs can be accessed. Primarily, the easiest channel is DVCS. That will be the focus of lecture 2 tomorrow. So how to do that with DVCS, but also through many other channels, and in particularly electroproduction of mesons at high momentum transfer. And that would be the topic of the lecture 3 tomorrow. So these are what we'll be dealing with tomorrow. So I will stop here, and then if you have some additional questions, I'll be happy to answer.
Thank you very much, Carlos, for a very interesting lecture. Perfectly timed. This was the expected time of 50 minutes. So we can open the discussion for about 15 minutes for question, comments, and I will start now. We have several hands raised. Let me start with Andrew Dodson. Go ahead.
Hi, do you mind going back to, I think it's slide 15, where you discuss, or you bring up polynomiality? My question has to do with, sorry. I guess I'll let you get there
18,
first.
yeah.
Yes, so when we have this virtual photon interacting with the struck parton, I picture just an electromagnetic interaction, but I understand that as a result of polynomiality, one of those coefficients ends up being the so-called D term, which is a form factor of a, to me, seemingly unrelated current. Do you have any, can you provide any intuition for why the form factor for a completely different current would show up as a result of polynomiality?
So now the D term is not exactly, I wouldn't call a form factor. So the D term was first introduced, and I think I will cover that a little bit in lecture 4, but it was first introduced to actually fulfill polynomiality in some models that couldn't do it, right? So when you start with to construct a model by double distribution functions, and we'll see what that is in a few lectures, then the polynomiality is not verified in the full range of X. So there was an additional terms that was added to fulfill that. Then it was found to be related actually to a subtraction constant in dispersion relationships. So dispersion relations are a way to relate the imaginary part and the real part of these GPD integrals. So you can relate the one with respect to the other through an integral plus an additional constant that it's called the D term. But it's not a form factor the way I introduced them before. Now, given intuition, physical interpretation of polynomiality, I'm not sure I can, if that was your real question, that I'm not sure I can answer and give a physical picture of why it should verify this constraint.
I see. Yeah, I bring it up because if you brought up the electromagnetic form factors, which if your current is the E&M current, that's how you parameterize it. And I think if your current is the energy momentum tensor, then you parameterize that in terms of form factors, and one of which is the D term. So that's why I call it one. I don't know, maybe I'm misspeaking, but yeah, I just wanted to know why that would pop up in this other process or this other interaction. But. Okay,
Yeah,
well, thank you.
I mean, we can discuss a little bit about the D term. I think it's Friday, but I wouldn't call it a form factor. Maybe we can discuss that again later.
Sure, thank you so much.
Next raise hand is Simone Venturini. Go ahead, Simone.
Thank you very much for your nice talk. I actually did not catch what is the physical interpretation of the Compton form factor. So the one which is related to the GPDs is in a sense related to the electromagnetic form factors, or is an independent object? I did not catch this.
Yeah, it's kind of independent, I would say. It's a GPD integral, basically. So, so it's not a form factor the way it was introduced at the beginning. It's some generalization of a form factor. So it's basically, you get a GPD here. This integral is what we call a Compton form factor. The reason is that the cross-section, the DV6 cross-section is written actually as a function of this kind of integrals. They appear all the time in the cross-section. They don't appear, the GPDs don't appear directly. They appear through these convolution integrals. So just the name, a generalization of the name of form factor to Compton form factor. So they are complex. You have this real part, which is the principal value integral, and then the imaginary part, which is the so the physical interpretation, it's a little bit given here as much as we can do. So if you have the GPD function, so this is the GPD H in one particular model, so the Compton form factor, the real part of the Compton form factor would be related to the integral of this GPD function along X, and the imaginary part of the Compton form factor will give you the value of the GPD along one line X equal psi or X equal minus psi. So you can either sample this distribution by slices, basically integrals of along X, or points along one particular line. So that's a little bit the interpretation that one can make.
Okay, thank you.
Thank you very much. Now we have a raise hand by Daniel Adamiak. Go ahead, Daniel.
Thank you. When you spoke about the spin sum rule, you said that we can get the angular momentum of the quarks from an integral over these GPDs and at a particular limit t equals 0. But you also said we can't measure these GPDs at t equals 0. And also I'm concerned about what happens at x equals 0. So you said we have to extrapolate these GPDs in order to try and calculate JQ. How do you know that we can trust any such extrapolation? Like, how do we know that at some scale, new physics doesn't enter? And so, yeah, how do we know we can just stop measuring at some finite t and say, okay, we can extrapolate from here?
Well, I mean, there's no answer to that question. I mean, you need to measure as much as you can, right? And then the more data you have, the better the more confident you will have in your extrapolation. But there will be always a little extrapolation at small t because you cannot measure that region. Now, there is principle nothing new physics that are gonna happen at low t. This is just a kinematic kind of variable, the momentum transfer, right? So, but yes, there will be always a kind of a model dependence on this extraction of the angular momentum. You can try to quantify this this model dependence as some kind of systematic uncertainty. So you can, what you usually do in this kind of extrapolations that don't only happen in this problem, but generally in physics, right? You check with different models, different assumptions, and you can then estimate how much your extrapolation changes, and then you kind of assign that as a systematic error of your extraction. But unfortunately, there will always be a model dependence for the two reasons you said, right? The extrapolation on X, on T, and then the fact that you need to integrate over the full range in X, and that's also something that you will never be able to measure experimentally. So there will be some model dependence or some systematic uncertainty, if depending how you want to call it in this structure. The only thing we can do is measure as much as we can. The less, the more data we have, the less uncertainty or the less model dependence there will be, but there will be always a little bit of model dependence in this structure.
But you're saying in principle, you can put an upper bound of how much uncertainty there is.
Well, you can by doing, I mean, what I just say, right? So you can play with different models. I mean, it will not be a strict bound. It will be with some assumptions again. So you can play with different models, and you can see how much things change, and that's a thing, the thing you can do.
Okay, thank you.
Thank you very much for your question, Daniel. Now we have a raised hand from Matteo Ceruti. Go ahead, Matteo.
Okay, thank you. You tell that in deeply virtual Compton scattering we cannot have chiral odd GPDs. I think that this is due to the fact that the cross section must be chiral even. Must preserve the helicity, must conserve the helicity. But can we see, and we cannot have another object, another chiral even object that can preserve the helicity with another chiral odd object. But can we see a subleading twist effect with chiral odd GPDs?
Yeah. So what? Okay. So you're right. So what I meant is that at leading twist, the leading order. So this diagram doesn't involve transversity GPDs. If you include additional higher twist and additional diagrams, yes, they do appear. So what I meant is that at leading twist, they only appear. These 4 GPDs.
Okay. Okay. Thank you.
Thank you, Matteo. And now we have Victor Martinez Fernandez. Go ahead, Victor, please.
Yes, actually, my question is related to the previous one. You said that these H and H tilde GPDs are preserving helicity, right? While E and E tilde do not.
Yes,
yeah?
That's right.
Okay, so my question is
the nuclear helicity, yes.
Yeah, the nuclear helicity. So, but my question is, how do you know that? I mean, what's in the theory or what's in the framework that allow you to see that the H and H tilde preserve helicity while E and E tilde do not?
Well, it's kind of by definition, right? So you construct the operator, and there are 4 that you can 4 different terms, and then the one that preserve the helicity, you label them H and H tilde, and then the other 2. So it's it's by looking at the operator. So I can maybe show tomorrow a little bit more details if you want to.
Okay, so the thing would be that, for example, the operator that goes with the H would be, for example, parity invariant and therefore helicity conserving, maybe?
Yeah, so yes, as you say, so it's going to be a helicity conserving operator, and then you will have another one. So I can show tomorrow. I mean, I wasn't planning to, but I can show a little bit more details on on the operators that define each of the GPDs.
Yes, that would be lovely. Thank you.
Yeah.
Thank you, Victor. In principle, we reach, it's almost 12:30. That is the cut time. We could stay maybe 5 more minutes if Carlos is okay with that.
Yeah. For me, it's okay. Yeah.
So we have, I would advise we have three more questions in QA with a raised hand. So I will go with those 3 and we stop the session. And we also remind you that you can also put some questions in the Slack channel and maybe they can be addressed there also. So I will continue here. Next question is by Andrew William Denniston. Go ahead, Andrew.
Great, thanks. So regular PDFs can be applied to gluons, even though you can't use DIS to actually probe them. Can you do the same thing with GPDs? Is there a gluon GPD object?
Yes, of course. So I will maybe touch on a little bit on the last lecture. So these are defined for any parton. So they are for each flavor of quarks and then for gluons too.
And what kind of interaction would you need to probe that?
Well, they appear with DVCS too. So you will have a gluon here, and then it will couple to the electron through a quark loop. So you will have one gluon on this initial state, one gluon on the final state, and then a quark loop to couple to the photons. So that's the leading diagram that appears where gluons appear. At higher twist, you can also have gluon coupling in addition to the quark, right? So you can have higher twist corrections, so higher order diagrams. But the leading order diagram with gluons will be through a quark loop coupling to the lower part.
Okay, thank you.
Thank you, Andrew. Next question is by Rafael Fernandez de Castillo. Please go ahead, Rafael.
Yeah, thank you. First of all, thank you for the very nice talk. My question is regarding, well, GPDs. You have been talking about how these functions provide like 3D knowledge of the parton distributions inside the nucleons. And recently I have been studying TND PDS and TND fragmentation functions, and they also provide some 3D knowledge of the parton. So my question is if you can comment a little bit in the difference between these two functions, because I mean, I think in some sense TNDs are connected to initial or final state, but GPDs seems to not be linked to any initial or final state, or be linked to both. So if you can comment a little bit on this.
Yeah, so I didn't comment too much because I think you have a dedicated course on lectures on TMDs, but basically the difference, the TMDs will be a fully three-dimensional imaging on momentum space. So you will have the image of three-dimensional, but on the momentum space, where as I explained here, the GPDs give you one dimension of momentum and two dimension of position. Now they can be related, the ones to the other, through some more generalized functions, the so-called Wigner functions, that they're kind of a little bit theoretical in a way, because you cannot access them easily, at least experimentally, but you can start from a general 6-dimensional function, right? And then depending of if you integrate some of the variables and of the momenta, you will get, you can find your GPDs, and if you integrate your coordinate space, you will go to the GPD. So they can be related through a more general function, but basically they are different in the way they probe the structure.
Okay. Thank you.
Thank you, Rafael. And the last question of the session is by Well, the hand was raised by Arjun, but I don't. Are you there, Arjun? No, looks like it's gone. So, well, in that case, thank you very much, Carlos, for the
Thank
lecture.
you. It was very good. Lots of
Thank you very much
questions.
for staying in the lecture. Enjoy your lunch or dinner, depending on where you are. And see you in an hour.
Very good. Thank you very much. And talk to you tomorrow.
See you tomorrow. Bye.
Bye-bye.
Sorry, Juan. Do you see Zhang Wei online?
I'm looking.
No, I don't.
Yeah, I don't see
okay.
it either.
Neither Alberto is still. Okay. Just wait a bit.
Yang Wei, I can see that you are here. You are as an attendee, you should be as a panelist. So I don't know if there is some issue with your link.
I just pulled them over to the panelist side.
Great, thank you.
Got it.
Yang Wei, are you there?
Yes, I'm here for some time and I cannot do anything. I cannot see, cannot speak, no voice.
Oh, because probably you entered with a link, with a general link that is just for the webinar. You could not participate.
Okay.
You're here now. Great.
So finally you discovered me. Sorry, I was screaming and trying to get
No, I discovered you because I see the raised hand. So, okay.
Then finally I can figure I raised my hand, my help.
Great. That you're here. So, well, I don't know. We are, is one
Yeah.
I don't know if you want to start or give some more minutes.
Yeah. No, I think it's better we start because we are already a bit late. So I don't know if Alberto wants to start. He was here.
Yeah, we are 2 minutes late. Now let's get started.
Yeah, okay. Okay,
So,
so
welcome back to eHugs 2021. And as my name is Alberto Accardi. Most of you know me by now. And my co-chair is who? Alex, you co-chair?
Yeah.
Okay, great.
I will be around also.
Thank you. And as a reminder, Hug students, feel free to raise your hand and then unmute yourself when we recognize you, or to write your answer in chat. All other attendees, you are very welcome to write your questions in the Q&A panel, and we will monitor that and ask the speaker a few questions at the end of the presentation. So today's speaker is Zhang Wei, who will continue, Zhang Wei Chu, who will continue his lectures on Introduction to Quantum Color Dynamics. Zhang Wei, please go ahead.
Okay, good. Thank you. I'm going to try to share the screen. Okay, I hope you can see my screen.
Yep, looks good.
Okay, good. Let me move these things away. All right. Well, it's a good, thanks for everyone to coming back. Then this is the third lecture of my total of 4 lectures. And I have to apologize. I didn't get any time to respond to your questions, but I will definitely respond it. Don't feel bad about it because I was in meetings, whole day yesterday and today. And So I will try to catch up things. Then I was told by the organizer there will be some kind of recitation or recap sessions. So I can also answer your question there, but I will try to catch up with the question tonight or tomorrow. Okay, this is the third lectures of my talk. Oops. Okay, so now it's okay, very good. So the last two lectures, I start to introduce fundamental things about QCD, starting from the the hadron particle to quarks and eventually gluons, then the QCD, then coming back to say what we can calculate. We start with a few fundamentals of QCD and also talk about the so-called this infrared safety, which is very important. Without infrared safety, QCD perturbation theory does not work. Then, so I started with a process with no identified hadrons, means you have a total cross-section or energy-energy correlation, or the jets, because you don't try to identify a specific hadron, in particular their momentum. So that you don't have a fixed momentum, you don't have those collinear divergence. So that's a part of the reasons. So today, we will go through the process which have identified hadron, because we really want to learn these hadron structures and also emergence of hadrons. So it's better to have observable connected to the identified hadrons than how we can handle it. At the end of the last lecture, I told you the way we do it, because we never see quarks and gluons in the real in the isolation, any modern detectors. What we do is we collect the data, which from the cross-section, we think they are good cross-section because they can be factorized in terms of quantity we're interested, those universal quantity, which will give us information on the hadron structures, or like a fragmentation fund give us information on emergence of hadrons. So those are data. Also mentioned from the lattice, we can calculate certain quantity on the lattice, although they are not directly related to the quantity we are interested in terms of like correlator or these functions, but we can factorize them into the PDF or GPD or TMD things. So that's one side data. Then also from other side, we have factorization, have a theory, have to prove to connect those things you have data to the quantity you are interested to have. You can have structure part, you have a PDF or the GPD, the imaging, I will talk more about it, and also emergence of hadronization part. So what we do is, because this is a standard inverse problem in the mathematics, then we cannot solve it directly, because it's nonlinear. So what the idea is, we do the so-called global fitting. We start with taking advantage of statistic mechanism learn or the AI or machine learning technique. We start with some try functions that eventually machine do the global fit, then extract whatever the collecting, you get the right information of the hadron structures. I did give you some example like a Poisson distribution function, one dimension. We are also now moving to state to the two-dimensional transverse dimension structure of the hadrons. So this is the tool you can do and the general approach we're going to take. So the question is, to achieve that, for any measurement, you really need to understand the factorization to understand how to connect the universal property, which it really only depend on the hadron itself, whether it's a pion, kaon, or proton, does not depend on specific process involved. Then how you extract them. To extract them, you require this factorization, how to connect these two together. So start with the process with one identified hadron. As I told you last lectures, there are a couple examples. I start with the electron hadron process with one hadron in the initial state. You sum of all the final states. So you start with electron, collide with the hadron. Only thing you measure start with a scattered electron, which is just like a Rutherford experiment. Instead of using electron, Rutherford used, say, alpha particle on a go-forward. So in this case, it's a quite inclusive process. You have one larger scale is defined by the momentum transfers. So if imagine the electron part, as we talked last time, it's well known. So if you single with a one photon approximation, then what you deal with is a cross-section is really related to the virtual photon, in this case, scattered with the hadrons. So in terms of Feynman diagram representation, you can imagine with the interaction with one parton, then you can have radiative correction. You can interact involving multiple parton. In principle, you have infinite number of diagrams. The question is, how can we ever calculate these things? The ideas that I told you last time, the factorization, which is approximation. The idea is that this probe, the virtual photon, has such a large invariant mass. That means the interaction point is so localized, time take to that that for the interaction is so short, so interaction can be localized to a perturbative regime, then rest of the hadron is effectively frozen during that time, so then they can be treated as universal quantities. Then the quantum difference between what happened here, the short distance, and what happened here will be power suppressed. So that's the general ideas. Then how can make that happen? So I start with a specific process that goes step by step, like with you, so you can see nothing secret. It's everything is derived. You can see what the approximation we make around the way. So imagine you have electrons get out of the hadron. If I exchange one photon, so this side, you know, the QED, it's a fermion, so you bond or the vertex from this photon coupling, then the fermion. Then have a propagator. I take the Feynman gauge in this case. Then you have for hadron, we don't know the details, but we know there is an electromagnetic current, which will effectively interact with a charged particle inside the proton. So that's the amplitude. So you can square the amplitude to get your cross section, right? We learned the 1/2s of the flux. The half, suppose that is spin averaged here, the average of the spin. You have two fermions, so 1/2 each, then square. Then sum over all the other indices relate to the spin or average spin or the other quantum numbers, the matrix number square, then a phase space. So you have all the possible particles, each of them give you this Lorentz invariant phase space. Then this is a particle separated because this is the one you're going to observe. So then there is overall delta functions. So no secret, everything's here. So then you can write these in such a way, because you know the M, you square of this term, you can effectively write the square of the lepton part, square of the hadron part. So you have effectively leptonic tensor multiplied the hadronic tensor. So leptonic tensor is nothing but the square of this diagram, give you as a E squared times 2 pi with this quantity. Assume there is no polarization, the average spin average quantities. So then the real issue, all the QCDs coming from these W's, hadronic tensor. So then we know how they defined, because defining in terms of matrix, sum square, or the sum of the final state, take a unitary condition, eventually we can rewrite this in terms of the correlate of two currents, the electromagnetic current. I did put in the spin S into the dependence because later, next lecture, I will talk about polarized beam. So in this case, although we don't know what this function is, they have to be controlled by the QCD, but we know the QCD has certain symmetries. So we take advantage of that. We know the QCD is a strong interaction, conserve the parity and time, reversal invariance, and the charge conjugation. Then we'll reduce this, give you some constraint on the W functions. Then so you eventually can decompose, if the parity conserved, you can only have 4 scalar functions. From the vector you have, construct a tensor, your only vector you have is a P and a Q. 2 vectors, because the tensor you have a matrix G mu mu. So that's the only vector you can construct, give you the gauge, the so-called current conservation. And for this side, because antisymmetric for the polarized one, if you have a spin, so it's an epsilon tensor. So again, you only have 2 independent spin structure, the tensor structure. So that means without knowing anything about QCD, only thing you know the symmetry. Without knowing any detail of the QCD, say assume QCD obey those symmetries, then you will find the cross-section where it can be expressed in terms for structure functions, then depend on whether it's a polarized state or unpolarized. So no QCD parton dynamics used in these derivations. So now that we're going to say, what if I'm going to try to really want to understand the parton structures? So I like to dig into the details. So what I do is since I know the QCD, I can always express this W mu mu in terms of so-called partonic representation. So your photon interacted with a charged particle, that means a quark. Now you can interact with a gluon. Then you have other gluon. You have many, many diagrams. As we talked before, this diagram is in a cut diagram notation. So it's an amplitude and a complex conjugate amplitude. So then in the real experiment, you never see any parton of the quarks gluons. You have to integrate over the momentum of the parton complete for all the phase space. Then also the partons are all the virtual. So the example is because amplitude and complex amplitude, naturally this diagram will give you the perturbative pinch singularity we talked the last time. So in that case, for example, this diagram, integration of the K for all the phase space will be dominated by the region where the K square is sufficiently small. Although the K square may not be exactly 0 because they're non-perturbative physics here, but the scale coming from this hadron wave function is order of 1 over radius or the order of lambda QCD. So the K square is a small number. Compared to Hart scale coming here, the Q flows through this platonic interaction part, that scale is the Q square. So that means under the approximations that have typical K square over the Q square is a small number. So you can assume that whatever K entering this part as a short distance, as a almost on shell. So then this is exactly the argument. So imagine you have this top matrix element, then you have this propagator. Eventually you cannot do perturbatively. You always absorb the propagator of the line connected with the matrix element into this whole thing. Then whatever this platonic part does not include the initial fermion line. So in there, you can set the K square equal to 0. That's the general idea like we discussed last time. So now I'm going to summarize a few steps like what I did before, but a little bit more accurate. So start with say at collinear factorization means that not only the K square is small, because imagine you boost the Q square so large, you boost the hadron in the very large frame we talked the last time. It's whether it's infinite momentum frame does not matter. It's a sufficiently large momentum frame. Then in that case, you can have a much better intuition. So you will see those partons of the longitudinal momentum should be order of a Q, which is large, compared to transverse momentum, the typically 1 over R, that's a lambda QCD. So in that case, you can make not only the approximation of a K square small, you can also make approximation K transverse small, if you only have one large scale. So at the lowest order, so let's go through this diagram again. So you start from, this is the matrix element. So we don't know how to calculate. I can write in the formulae, the matrix element, I put in the momentum space, the K, I put in the position space expression, it's a Fourier transform of the position. The position is Y, it's a 0 or the Y. Now you have two fields, fermion field corresponding to this fermion line. I have a state of proton. So now on the top, I have a first vertex is gamma mu. Again, then the propagator, because it's a cut line, the rule for the cut line, instead of normally you have for fermion, you have a gamma momentum in the numerator divided by momentum square. The cut diagram effectively take an imaginary part. So you end up, you take this twice 2 pi times the delta function on shell conditions. This can be derived. Then this on shell condition, if you work it out, actually directly tells you that X, the momentum fraction is equal to K plus over the P plus. So this is the lowest order diagram. So I want to do a little bit general. I can write these as H mu mu, write these as say F as a functions, which represent this bottom part. Then I can say, do exactly what I told you before, make approximation of the K in these H, because the only scale here is a Q, order of a Q. So make a K is order of XP, collinear part, neglect both transverse and the virtuality. So that by doing so, I introduce a 1, which is a delta function dx over these delta functions. So I keep the x integral here because this does depend on x. Then I move the d4k integral to the backside, including this delta function with this matrix sum. So the approximation I make is the factor of k squared over the q squared, kt squared over q squared. So the next approximation we're going to make is because this is a fermion, they have connected by a trace. So then if I think about massless case, this you can imagine it's a 3 gamma matrices. So the only one can survive if you do the separation of the gamma matrices between these two terms. You know the Fiat transformation, you have 16 gamma matrix bases, but only the single gamma mu term or gamma mu gamma phi related to helicity will survive because this has odd number of gamma matrices. So I decompose separate spin, that's gamma related to fermion spin. In this part, I have a half gamma dot px, then also separate the momentum. So this part, a trace going here. Whatever a projector operator put it in is order of 1. You say, well, wait a minute, there is a gamma, the p here, then you have an x here. Well, I divided by x. Often this is like a platonic, when you have flux, if you do the parton level, you 1 over 2s hat instead of 1 over 2s. So you have an extra x put in here. So I multiply x here. xp is the momentum k. So this is give me a real effective platonic cross-section from the top part. So this then, so now I can label these. This one I call short distance hot pot. Then this one I label as distribution. I give you the operator form in a moment. So you know you can derive that quickly because you know exactly the operator form defined. You can see 4-dimensional integral here, position, 4-dimensional integral momentum here. Then there's only one direction that connects to the x. So the 3-dimension can be taken care of by the delta integral over 1 with exponential, give you a delta function. So you end up with a matrix element with a position in only one directions. Then, so that's then I'll give it a detailed definition moment, but in terms picture is exactly the one you can imagine. So this is the diagram you start with. You make approximation. The platonic part is a momentum entering this platonic part is a collinear. Then this fermion will be contracted by half gamma dot xp, which is momentum k. So which is exactly sum of the spin of the u bar u. So that's exactly the little cross section. Then approximation you made is a k power over q square and a k square over q square. Then this convolution means the dx over x. Then this is the distribution is given here on next slide with this operator with this kind of projection. So you can see they corresponding to the distribution exactly the integral 3-dimension can be integrated over, except the one left is related to the x. So then you have the correlation of the two field living on the like column y minus or the y plus, y per, all zeros. So this corresponds to hadron state. But if you look at it, this matrix element we like to call the Poisson distribution, but it's not gauge invariant because these two fields at a two different place. When you make a gauge transformation, this matrix element changes. So what happens is you need a gauge link to make this to be the gauge invariant. So the real Poisson distribution is defined, is the same like these two Poisson correlator, but in between you have a gauge link. Then the question is, you don't put it in by hand. Then second is, well, because you close to the k momentum when you make this approximation on last slide, you make the d4k come all the way to the back. Then if you calculate this perturbatively, because you have a closed loop momentum, you will find you have additional ultraviolet divergence related to non-local operators. So this field, not only the field, but also this non-local operator needs to be normalized. So that is the UV contour term. So that's the exact definition of PDF. Then you say, well, how can you put it by hand? The gauge link sounds like you're putting it by hand. Answer is no. QCD has that. So I gave you one example. See, start with the diagram. The diagram we have not calculated yet. Say the diagram with instead of a 2, you have additional gluon. When you have a gluon connected, gluon is different from the quark. Not only have the momentum, but also has the polarization because of vector particle. So to relate to the gauge link is only the plus momentum dominant and the momentum component around the direction p momentum. So what we do is that we contract to the separation between top and the bottom. So look at the specific left diagram. I have a matrix M represent the bottom part. I have an integral of this loop. I have the position y1, this integral I'm going to do. Then with the moment, the x1 is the momentum flow through, then correspond to the difference of the position. And the n dot A is the A field here, I contract the n to this side, then other side with dot P, it's a gamma dot P, it's a unit. So then, so I have a vertex, then I have this propagator, this one, then propagator enriches this form, then denominator, interesting things, you write it, you will find denominator is a proportion of this pole, has a pole. Then this one you can, but it's not pinched, it's only single pole. So now you can do the integral of this y, then you, by using this pole, you end up with a theta function, tells you the integration from the y have to come in, when you do the x integral, they have the require, if you want to close the loop, make sure this does not give you infinity, rather give you a 0 in the infinity. So then you require this y minus 1 has a sign. So that means the y1 has to be larger than this, so you can close the loop. So then you add a constraint. So the integral of y is now between y minus to the infinity. Then you can do the right-hand side for this diagram. You follow exact same thing. You will find that corresponding to this position, the y integral between 0 to infinity. So now you add these two diagrams together. This is a part of your Feynman diagram representation of the contribution to this cross section. So you add them together. You combine these together. This is exactly the first term out of G term of your gauge link. I can leave to you as a simple exercise. You can prove then when you add all these kind of diagrams, if the gluon is a longitudinally polarized, when you add them all together, it exactly give you that gauge link, and not only give you the exact gauge link, but I also need this P, means the path ordering. So that's a very interesting homework. Then just go to 2 gluon, you will immediately realize you need the path ordering to do that. So now we have a formula. The distribution can be expressed in terms of this gauge invariant form. But what happened to the high order diagram this way? So I have radiation go to final state. So imagine we say this platonic had to be short distant, but now it's not necessary, because if the gluon is not observed, you have to integrate over all the momentum of the gluon. This propagator, if you imagine it's an actual dk1 over k1, you are all the way from 0 to whatever the Haas scale defined here. So when the k square is close to 0, this is like a pinch singularity situation, then it's not short distant. This cannot be short distant. But what we say is when the area close to whatever phase space close to this 0, this long distance physics, they should be absorbed into your definition of distribution. So you only leave the short distance part. How you achieve that? So for the diagram like this, so we do add, again, the standard trick, we add and subtract. So we say this is a diagram with the integral phase space. I'm going to break into 2 parts. The phase space is below this factorization scale. Remember we talked last time how you factor factorization scale. Then we say this part should be included in the distribution. Then when the part is close to order of a Haas scale, they should be short distance Hall part. So then you can make approximation in this case because the scale is so small, so like a collinear. So really short distance Hall part only the top line because these 2 propagators are almost on shell. So you have a lowest order Hall part convolute this part contribute to actually the scale change of your distribution functions. Then for this one, because the whole thing is short distance, you can put in this whole thing as order-wise correctly short distance. So you have a lower order distribution functions. So you can effectively put this term as a lowest order C function, convolute distribution function at order of 1 correction, and this. So when you add them together iteratively, you can also prove in a more general way. But if you do that, imagine you have all this diagram, end up with some of the short distance expansion of alpha S, multiply all these collinear things order by order, you include them into the distribution function. Now the distribution function depends on scale. So that whatever physical quantity, in this case, a structure function with proportional something you can calculate at order of a Q to between the Q and say factorization scale, then multiply a distribution function dependent scale. So depending on how much you include them. But you say, well, wait a minute, this is too much because it's so ambiguous because I can choose anything I wanted, but there is a renormative group equation to help you to control that, to make this sensitivity to be very small, because you find that the physical quantity should not depend on the choice of the mu f. If I take the full derivative of that, I can derive the renormative group equation. Before doing that, I gave you the picture of what the factorization means. In the sense, it's really the time evolution. Imagine you have a proton come in, you have have one of the active proton collide with a virtual, very, very short distance virtual probe, then produce a many, many particles in the final state. Now you remember this, this is non-perturbative, right? But however, when you square them, when you sum over all the final state, those states unitarily canceled, end up with really short distance. This is very much like what we did for this E plus minus to hadron total cross section. You remember we have a virtual photon decay all the long distance final state term, but when you add all those final state together, they exactly cancel, end up with something very short distance. So this is exactly a picture for the factorization, intuitive picture for the factorization in the inclusive DIS. So then the interaction between the past that happened here is the past, and now that were taking place here is powerfully suppressed in that case. So then I go back to the formula. I told you this, we derived these in terms of short distance one, multiply distributions by apply the, in the sense, so I'm going to tell you, you can derive take a full derivative that derive the evolution equation of these distributions. So make the scale dependence as predictable from the theory, except input distributions. So that's why I make the factorized formula much stable, even though you have ambiguity to choose the mu. Okay, So now the question is how to calculate this perturbative part. We just gave an example. You like to have a prescription from this, you can calculate this to all order in perturbation theory. So the prescription is that when you have factorize the formula, this part is short distance. So this part should not depend on what kind of hadron you have. In this whole derivation I mentioned, it's just hadron. The hadron can be proton, can be neutron, can be pion, but the factorization is more sensitive to the scale at the order of Q, not sensitive to scale at the hadronic scale. So if you can prove this factorization formula is true for any given hadron, in principle, you can apply this exact same factorization formula to the asymptotic parton state. Of course, because the parton has a zero mass, you may have a collinear divergence, but you still can have factorization formula if you have a regulator. So you can. So what you have to do, I apply this factorized formula instead of a hadron to a partonic state. So example, I apply the hadron to the quark state. So you have F2, a structure function on the quark. Then in this case, you find a distribution, a parton distribution within a quark. Then you can see the short distance part should not depend on. So, but the great advantage by doing so, this side is a Feynman diagram because you're on the asymptotic quark state. It's a perturbative calculate Feynman diagram if you can regularize the divergence. The same thing here, this is a Feynman diagram. The parton distribution, we said we cannot calculate perturbatively, but once you project on a parton state, just given by Feynman diagrams. If you have regularized the divergence, you can calculate. But whatever divergence from here and diverging from here, they have to better to be canceled because this had to be infrared safe. This had to be short distance. So this is exactly the idea to calculate all these coefficient functions to all order. We start from zeroth order, for example. So the left-hand side is the idea to expand this formula order by order in perturbation theory from left and right. So in this case, I have a structure function in the sense a photon scatter off the quark at the zeroth order strong coupling constant. Then this is the coefficient has a quark to quark. There's no fragmentation coefficient multiply this parton distribution. You find a quark within the quark without interaction. Zero means no strong interactions. They're better to be the delta function. It's no interaction. From operator definition you had on previous transparency, you can prove that it's just delta function. So what you find as a zeroth order coefficient function is nothing but just a tree order diagram. You can calculate scattering photon on the quark state. This is consistent to what we talked earlier. So the question is for the one loop. Well, the same thing, you apply both sides to the order of S. So left-hand side is just order of the structure function or the scattering of the photon on the quark state. But right-hand side, you can find you have two possible terms. You have a term, you say the first term is order 1, next term is 0. The next term is this coefficient is order of 0, this is the 1. So you can see that this one 0 is delta function. So you can always write the C1 in terms of F1, which is the Feynman diagram, which might have divergence, but you can regularize it. The minus term with the lowest order C, you already calculated, put it in, multiply one loop, but these are parton within parton distributions. So this may have divergence. If the factorization is true, the divergence from here and here better to be canceled. You get something finite. So this is exactly I'm going to show how to do that. Then so what happened is you have to learn, to do this calculation, you have to learn two things. One is how to calculate a parton distribution within a parton. Second is to really calculate the scattering, whatever physical part scattering, instead of scatter off the proton, you scatter off the quark or parton or gluon. So those are two things you need to learn. Once you know that, you can calculate this to all order. So quickly, I show how to calculate parton within the parton. It's just operator. We had it before, the correlator of the fermion field on the hadron state. Only difference, you replace hadron state, the parton state, asymptotic parton state. So what your difference is just Feynman diagram. If you take a lowest order diagram, you just take the operator, you take this lowest order diagram in the momentum space, you will find this is just a trace. From this side, the P, the half gamma, the P. Then this is the projection operator define this distribution function because you should divide by P plus, multiply the P plus here. So then the operator you really have is the gamma plus over 2P plus. Then when you integrate over the phase space, you have a delta functions. From an operator we define, you had it before in momentum space. Then you have these overall delta functions. Well, overall delta function take care of this integral. Then you end up with the result is just simple delta function. That's the lowest order. So you can calculate next order, just radius of the gluon plus virtual diagram. You can calculate, you say, suppose I do 4 dimension, you will see exactly you get a divergence. When integral over transverse momentum, when transverse momentum go to 0, you will have divergence. So that's exactly what we say the Poisson distribution is not perturbative. If you try to calculate them, you have divergence. But we try to regularize it. If the factorization true, the divergence come from here will be canceled. So I demonstrate, give you a more complete example how to calculate one loop, the coefficient, deeper industrial coefficient functions. So exactly you start with the projection operators, W mu mu, have these on the F1, F2, to speak average case. So I want to calculate F1, F2, either one of them. So you just simply take a projection, eventually from W mu mu. So then you can start with a factorization approach. So 0th order, I just expanded both sides to 0th order. So in that case, 0th order X mu mu contract with this diagram is nothing but delta functions. So you immediately derive the C0 for the F2Q is delta functions as we expected. So now the key is what we calculate first order. The first order is exactly you calculate this scaling the structure function of a parton minus 0th order convolute the distribution within the distribution at the first order. So then because I have to regularize, I use dimension regularization. So G mu mu contracted is dimension n. So then when I do that, do the projection operator to F, then we have to include the order of epsilon term. So instead of the projection operator you saw in the last slide, you will have additional piece depending on order of epsilon, because your perturbative calculated W will have a 1 over epsilon divergence. Then so now here is a calculation. This is just a scattering photon on the quark state. You have a real diagram, 4 of them. You have a virtual diagram. Then this is like your projection operator. You can put in the Mathematica to calculate this state. It's not complicated. And also it's instructive to calculate by hand, at least to do one. You understand where the divergence comes from, how things work. So you can calculate that. So when you find it, then also that's if you look at this expression, you need to calculate the F and also calculate this term, 2 things. So you can calculate, you will find this term worked out is a term proportional delta function, the virtual diagram. Then the proportional delta function. Remember I told you last time, you will have 1 over epsilon squared term, 1 over epsilon term, then that's fine. Then because we know there is a region where you have both infrared and collinear divergence, then you can do the real diagram calculation. Again, you have, I don't go through the detail, but you can easily find it from any textbook on QCD, especially John Collins' book, you can find it in that. So then the question is to combine them. When I combine them together, you have 1 over 1 minus x and 1 plus epsilon. If the epsilon was 0, when you integrate over x, x go to 1, you have divergence. This is exactly responding to infrared divergence. So when you have to do expansion, you have to expand in the epsilon. So this factor actually can be expanded in the 1 over epsilon delta function plus so-called plus distribution, which is defined here. It's when x goes to 1 will be something used to cancel that. It's a finite. So this is just a very typical QCD calculation. You have to deal with it. Then so final result, we combine together. It's a 1 loop case. You have all the epsilon term canceled with some funny looking this plus distributions, which is important, give you some threshold logarithm, but people might heard about that. But it's a standard thing. It's defined under integrations. But what's left is you still have 1 over epsilon. Because you have fixed external momentum, you measure that, so you can have a collinear divergence. If you do E plus minus to the total hadron, remember when you add a real diagram, virtual diagram, all the poles are canceled. But here, because I have one identified hadron, in this case, the parton quark, so I will end up with still the 1 over epsilon pole, but single pole because it's a collinear divergence. Now, coefficient of that is known as the splitting functions. So the question is, how can you take care of that? So the idea is that we have a structure function F2, have to take a other projection operator, combine the 2 together. You have final result is 1 over epsilon from a collinear region plus everything else is finite. When the epsilon goes to 0, go to infinity, that explained to you that this Platonic distribution, which is not perturbatively calculable. But there is a subtraction term. Remember when we calculate function, these short distance functions, where's my functions? sorry, I'm sure somewhere, then you know the short distance functions is subtraction of the two terms. You have this one distribution minus term proportional to the part distribution within the part term, so that you can see the divergence. So this one is this diagram, you have a UV divergence and a collinear divergence, but they're coming from the two different regions, but the UV divergence have to be the norm, right, by UV contour term. Then this is collinear divergence, when you add this term with this term together, they better to be canceled. So they exactly cancel. Then this introduces ambiguity, how you normalize UV divergence. Sometimes you remove the pole, or in principle, you can also change some finite piece. That introduces skin dependence. That's why people talk about the MS bar scheme for the PDF, because you calculate the short distance part, use a minimum subtraction to remove this UV divergence. Or sometimes people use the DIS scheme or other scheme to remove divergence as well as some finite piece. Then you get a different coefficient function, just means different scheme for your definition of distributions. So that's with that, we calculate, you have a short distance coefficient functions. So that's, you can calculate the two loop. But I told you before, you can also, because the physical classification should not depend on factorization scale. So you take a full derivative equal to 0, you will find the two terms. You have the first term, the second term. So immediately you know the C, you already calculated C. Take a derivative of that, you get to that term. So you will find the derivative of these. You derive the formula. Derivative of these will be controlled by, this is a perturbed calculable, this is perturbed calculable, this is exactly related to the coefficient, the perturbed calculable, the so-called de-Galapagos evolution equation. Change of a distribution with respect to the scale is a proportional distribution times the perturbed calculable. So although there are a lot of ambiguity to choose the factorization scale from the theory, factorization theory, you know, it's a so-called renormalization group improved expression, then the ambiguity on the choices mu f actually have a small impact on the physical observable because they compensate each other. Okay, so then the evolution kernel I showed you early, this is evolution of the kernel. How do you calculate this kernel? You can calculate this kernel, of course, is from the definition of the, you know, take a derivative of C, but also you can calculate directly from this operator definition. I'll give you another method. The method you say we do know the distribution is defined to an operator. You put the radiative correction to it. You calculate the derivative of the change of the scale, then proportional to the distribution itself. You just factorize this bottom part out of it. You can derive it. You will find the real diagram actually have a so-called the distribution times the spreading function part is a gain because you change the, imagine this is the place you do the observation. After radiation, you see this quark, but imagine you, this after radiation, you know, the quark goes away, so it's a subtracted negative term from virtual diagram. Actually, you can imagine these two formula is look like Boltzmann equations. The change of the number density, including the through the interaction, the gain part and the loss part. So this is also interpretation for these Poisson distributions. Then this can apply to all order, at least the valence part. So that's an interesting part. Like one complete example how to calculate these coefficient functions. Now we need to go beyond one hadron. What about you have two hadrons? This is the factorization formula we have because we know the quantum difference between this guy and this guy is power suppressed because this scale here is order of Q. This scale here is order of 1 over R. What if you have two hadrons? Imagine the Joule-Yang process. If two hadrons collide, produce a short distance virtual photon, decay into dilepton pair. So immediately you realize the trouble. The soft interaction between this hard part and this will be power suppressed. What happened? You have a soft interaction between them. The scale here is the 1 over R, scale here the 1 over R. What happened to this guy? This is exactly the most difficult part of proof of factorization. Then took people actually a long time to prove it, about over 20 years by this one specific configuration. In my backup slide, there's 4 slides summarize all the key steps you needed to prove the Joule-Yang factorizations. So here I give you intuition. So imagine this is a hadron goes to virtual photon, go to final state. So imagine you square them, then you can see this line with a complex conjugate, you have a pinch virtual integration. Same from this side. So naturally you can think of square of the top part, square bottom part, multiplies square this part. That's exactly Joel and Yang initially proposed. We have a Poisson distribution from one hadron, convolute the Poisson distribution from another hadron, multiply a short distance Hall part. They proposed a formula. So then you have the formula in their original paper. Then that time, because the Joel-Yang formula was proposed before the QCD actually invented. So they just have a formally is a Poisson model picture. So you have two distributions, you work out the Platonic part, then this formula is actually almost right except missing color factors. So if you compare this formula with experiment data, you will differ by a factor, 3 times the K factor is like a factor of 6 difference. So then, what happened is eventually when you add them together, there is a color factor. So you will find it, the result is very, very consistent. But the proof of the factorization is hard. When you go beyond 2 level, you can have interaction between these guys. They have no large scales, and the virtual soft photons, the vector particles, the long range. So how can you justify these two distribution can be universal? You have a hard collision, soft interaction, long range. This interaction may distort the distribution. Then you still have a hard interaction, but distribution is no longer universal. So I give you the intuition, the proof in one of my paper earlier about the proof power correction of factorization. So idea is that you do have soft gluon, but gluon have all kind of polarizations. Physical polarization is transverse polarized, longitudinal polarization often is non-gauge dependent component. So what happened, imagine you stay as an observer in the one of the hadron, the other hadron coming very, very fast. Whatever vector field coming from here have to suffer the Lorentz transformation to when they arrive here. So then the gauge field, the component in the longitudinal direction, does not Lorentz contract. So and the Lorentz transformation is order 1. So this gluon will interact with you way before the hard collision takes place. But luckily, those are gauge dependent. If you work a gauge invariant quantity, unitarity and the gauge invariance help you can remove these. But if you look at physically polarized component, you will find actually this field will be strongly contracted, actually down by 1 over gamma square. This actually gave us a reason in the paper I wrote with George Sturman in 1991, you can actually prove the factorization up to the 1 over first non-trivial power correction at the 1 over q square for a spare average case. So then that's the reason. So on my backup slide, you will find a few key step how to prove that if anyone interested in it. Then the formula finally, if the QT, if local transverse momentum, if the transverse momentum is so much smaller than Q, it's a 2-scale problem, it's a TMD factorization. You will hear a lot from Andrea Signori about TMD factorization. But if the QT order of Q, it's a single scale problem, it's a typical collinear factorization. You have 2 distribution with a short distance Hall part. If you calculate individual diagram at the radiated correction, you do have a divergence, but when you combine them together, divergence is canceled, give you a short distance Hall part, the infrared safe. So now I like to go even beyond. Go ahead.
There are only about 5 minutes left
Yeah.
because we want to take
Sure, I will try
the
to
discussion. Is it okay?
Yeah, thank you. So the factorization for more than 2 hadrons, so you have not only the initial state hadron, but also have final state hadron. Then that proof, actually that a lot of people use that. The first complete proof in my paper with my collaborator in the context of Kokonia production, if you have observed a single hadron in the final state. So not only we prove that the leading power in the 2 Poisson distribution convoluted with 1 fragmentation function with short distance Hall part. We actually proved a little bit further to the 1 over q square correction, 1 over pt square correction factorized. So that's good. So now finally, once you have all the factor formula, how can you extract the distributions? Well, it's a global fit. You have a single hadron case. This is what you measured. This is what you can calculate, but this is a function you don't know. But the 2 hadron case, this is what you measured. You have 2 distributions, then you can calculate, and also you can have fragmentation. So then the distribution obeys the DIRAC evolution. So what we do, we give an initial distribution at some scale with some parameter, then evolve, then plug into this theoretical formula, calculate your theoretical prediction compared with the experiment. Then you calculate chi-square. Of course, you start with a tri-distribution may not be good. Then you compare the experiment data to global fit, eventually end up with a much better parameter. This approach can be very different. There are a number of approaches, but the basic idea is similar. Start with some tri-functions, then eventually they derive the 2 input distribution then you can have Ruri prediction for the experiment for wide range. So this is like a distribution people have from lepton data alone, start with 2 GeV. Then this is a result of a global fit. Then there's a width of error because the data has error. Then you will find that at the end of the day, you have some constraint because valence quantum number is conserved and the momentum is conserved. Those are the constraints involved in your fit. So this is an example of how good the theory and experiment for many order of magnitude for the deep elastic scattering structure functions. And also I showed this to you last time. You not only do the single hadron, you do the double hadron, you know, the LHC case, that you have more than three, almost 4,000, you have 3,000 data points. And as I explained to you last time, we have to next leading order, chi-square is very much consistent one. This one shows again, emphasize it's a 15 order magnitude inside the cross-section. Theory and experiment are very, very consistent. This is what I mentioned to you last time because this is connected to a talk you were here in this school. The 2-scale problem, I explained to you, this is a completely new class observable, you know, to the 3D structures. So you are here from a TM example. I want to use a minute to emphasize the difference between different facilities because we like to have a 2-scale problem. That's what I told you last time. But around the world, you will find you have E plus minus collider, but in this case, you have no hadron to start. So this machine will not help you to study hadron structure, but will give you a chance to study the emergence of hadron from final state. But if you look at the hadron-hadron collider, REYES or LHC, you do start with the proton. But Hawk collision, most observable, you're interested in the proton is broken. You break a proton, then your proton interaction look for a final state. But once you broke on the proton, you know, you generate a lot of gluon shower. So the typical structure transverse momentum distribution observed, measured in this Hawk collisions is not the same as a confined motion in a bound state because there are a lot of a shower generate the transverse momentum. So it's not ideal actually. So it is a lepton-hadron process. You have a scattering, you have a chance that not only you can break the proton, but it's a much smaller phase space, more precise measurement. So you can have a better, more close to the edge of, you know, more close to the energy scale of your hadronic wave function. So you can see that really getting more information on the confined motion. And also you can have situation without break proton. That's very, very important. You can have a larger scale because in the hadron collection, larger scale get more or less break the proton. But in this case, you can have a large scale from the virtual photon to diffractive without breaking the proton. If the proton is not broken, then whatever structuring for you measure, it's a really true structuring informations. So that's why lepton hadron is unique. Then, as I mentioned, there are 3 type process. One is inclusive, like Boltzmann, a Rutherford experiment. You measure all the final state. Then that case gave you a single Hawk scale. It's good for the distributions. But if you measure additional particle in the final state or jet in the final state, you really see the 2 scale. You can measure transverse momentum dependent upon distribution. So get information on the confined motion of a quantum inside the hadron. Then you have, without breaking the proton, look for a single particle final state. You really try to see the diffractive process, get information, sort of 3-dimensional imaging, in this case, the spatial imaging of the proton inside the hadrons. So the EIC, the future, then this is I want to just give you a picture. What the EIC can do, it's like a CT, it's not in the hospital, but you CAT scan a proton on the nuclei, try to see the internal structural imaging of the proton and the nuclei. And at the same time, the EIC also have a probe. I told you last time, you can, if you large Q, the transfer size is very small, but if you go to small X region, unfortunately, we're not going to talk that much, the quantum fluctuation of this probe in the longitudinal direction is not localized. So actually, when the X is much less than 1, then the uncertainty of this probe can be the same size, or even bigger than the Lorentz contracted the proton size. So you can see the long-range correlation. You can see the wave nature of the gluons. So that's it. Let me finish here. So actually, I finished a minute before the 5. Anyway, any questions?
Thank you, John Wei. We should give him a round of applause for keeping in time. So you can unmute, repeat yourself, and give an applause, and also for the good lecture. For everybody. Okay, now. Oh, thank you. Okay, I already see a few raised hands in chronological order. Andrew, please unmute yourself and show us. Okay, yeah, that's great.
I have a quick question. So I saw how you defined it when you just switched the hadron state to the parton state, but can you elaborate a little bit more on what is meant by a quark in a quark? I have a hard time picturing that.
Oh, sure. You just imagine the quark is, because we are dealing, when you do the perturbation calculation, you have the interaction pictures. So the quark field, you can imagine, is just a free field. Because I say this is asymptotic state, because it's like a collision, a quark state is, say, time in the minus infinity. So it's a free quark. So when you do the calculation, I go back to this expression. I calculate distribution within the distribution. Yeah, for this example. So this example, imagine this is the quark field, initial quark state. What I have is just a U bar. Then in this, depending on which direction, the U bar and the U. So what happened for this K is sum of the U bar, U for momentum K, sum of the spin for this part, because this is given the projection operator, which is consistent with that. Then this part is an incoming quark state. Imagine you have a U bar, U sum of the spin, which is a half gamma dot P if I average of the spin. So that's for my half gamma dot P, which is sum of the spin U bar P U P, then divided by half. So that gave me this one. So this is the projection operator defined by the distribution. That's the operator. You should divide the P plus here, the multiply P plus here, corresponding to this Fourier transform. So then you have a vertex, go to the U by U, sum of the spin, that's half gamma dot P, the trace, then that's a definition momentum space overall K, then the overall momentum conservation, and this is delta function from a vertex cutting sort of a PDF definition. So you end up with this. So you treat the fermion field, in this case, as a free field.
I see, that makes sense. Thank you.
Okay.
Victor, please go ahead.
Okay, so in the slide number 8, you were introducing number 8 when you were talking about the gauge link.
Yes.
You said, maybe I don't hear it, but why is the n times gauge field?
Oh, sure. Yes. Just maybe I didn't write it. What's n? N is a Lycon vector defined have a minus component 0, 1. If I use the vector is a plus minus per 0, 1, 0 per. So the n contracted any vector you pick up with plus momentum. So the idea here is if you look at the gauge link, definition is A plus. It means A dot n. So that's a piece you want to pick it up from the diagram. So then when I have this diagram, next slide. So you have the A field sitting here. Have a Lorentz indices say A alpha. Then this gluon has alpha. So when I decompose them, say I want the piece A plus. That means I have to contract with A dot n. So instead of contract all alpha from 0, 1, 2, 3, project this A dot n piece, then correspondingly, is like projected to the bottom part, is corresponding to the gamma dot P over P plus. So the gamma dot P over is a P in the direction of alpha divided by P plus. So that if that where you contract the n, that gives you 1. So it's that's I don't pick up the full diagram, not the A with all the components. Actually, this diagram contributes to its full contribution if the alpha, if the gluon the transverse polarized. But here, what I'm interested is the gluon is in the direction of a plus. So I have a n dot A here. So contract this side. For the platonic side, correspondingly is a P. So P contracted with alpha, gamma alpha here. So that's a piece corresponding to this vertex. Now you have this propagator. I'm just putting the propagator in this momentum fraction form. Now you can see explicitly the pole. So I do the integral of this x integral, take the pole, it gave me a theta function. The theta function gives the limit on the y integral. So the y integral, y1 integral is limited to larger than y minus.
So you need that precise component, this plus component of the field, just to get also a plus component on the quark that is propagating between photons.
No. If this A plus, that means this will contract to, have a P plus, pick up the gamma minus in that sense, actually, the plus minus. The P has only plus component. So I contract this vertex by plus. Then you have a gamma minus sitting here. Yeah. So unfortunately, this time lecture, only 4 lectures. If we go to high twist, you can see, actually, I have a paper in 1990, goes through the great detail, show this group diagram, you have a component, you have a gluon can have a longitudinal polarized, transverse polarized, as well as minus direction polarized. So then you add them together, you can break this diagram in different pieces. They have a gauge invariant subsector. So you will find this piece we just talked about here, we combine the lowest order diagram with the gauge link. But when this gluon is transverse polarized, that's exactly give you the part of the twistor 4 contributions.
I don't know, I don't still see why that precise component. Why, I mean, even in the Wilson line, in the link gauge, why just the A plus?
No. What I do is just derive the Wilson line for you. Wilson line is not put in by hand, just from the diagram. So I just derive the Wilson line contribution for you. That these 2 diagrams will have a contribution to the Wilson line, and the one coming from this way, another one coming from this one. We combine them together, is it give you exactly Wilson line connected to these 2.
No, I understand that you need the A plus component in order to at the end get the form of the gauge link, but I still don't see why, for example, the negative or the transverse components do not.
Oh, they are there. They are there. I should put add here the other component. They're all there. That's why I mentioned. If I try to include all these diagonal contribution, in the paper I wrote that exactly say every single Feynman diagram contribute to every single twist, actually, amazingly enough. Even the handbag diagram contribute to all twists. So this diagram, as it stands, will contribute to all twists. So what happens is that the longitudinal component part contribute Wilson line, give you a leading twist. Even after that, when you separate the trace between top and bottom, we have high twist contributions. But this diagram, just in my shorthand notation, I didn't write carefully enough. So this diagram should be approximately equal to gauge link part plus other term. So in the sense that this diagram can contribute to all twists. The transverse component will contribute to the high twist contributions. Minus component also contribute even higher twist contributions.
Okay, and then why? How do you know that the dominant one will be the A plus?
Oh,
and the transverse or the not?
No, I don't know, but I can prove it. But in a way, because I can suggest I sent you a reference to my paper in the 1990, which exactly goes through all these diagrams, show then which polarization will contribute to which twist.
Okay.
It's in my paper. It's a 1990 a Physical Review D. My name, single author. You can find it easily.
Okay, 1990, right?
Yes, 1990.
Okay, thank you.
Yeah.
Okay, Matteo, please go ahead with yours.
First of all, thank you for your very nice lecture. And I have a question about slide 21.
Okay, sure.
When you talk about the problem in TMD for the factorization with 2 hadrons identified. But I didn't catch very much the problem. Is that related to the so-called initial state interactions?
Yes. Then it's exactly, because imagine, look at this diagram. So you have a hard collision, say it's a time equal to 0, because a 2 hadron coming from a t equal to minus infinity. So then before the hard collision take place, then you can exchange a gluon, soft gluon, initial state.
Okay.
So maybe I can show if I gave you a backup slide for any theory student who are really interested. I have 4 slides. 4 slides. Yeah, 4 slides summarize all the exact key steps you needed to prove the factorization for Joy Yang. So this is the lowest order diagram. You can identify the leading component and like pinch singularity tells you. But the point is, when you go beyond that, you can have a soft gluon, all the soft gluon, connect to them. So what happens is from the argument from power counting, you only two type of the gluon give you leading power. It's related to early questions. How do you know why they are being important? You can prove that when the gluon is longitudinally polarized, when they parallel to incoming active proton, they are leading power. And the other gluons are very soft, then those soft factors. The proof factorization for the first part, gauge link part, just like we did to find that related to gauge link, it's a straightforward very quickly. So people immediately write down the factorization formula. Then the rest, the difficult part, exactly soft gluon connected by between the two hadron, between the spectator, known you can be trapped. This loop can be trapped into so-called global region. You cannot deform contour out of it. So it took literally 20 years for people to eventually prove Joy-Yang cross-sections. Then for the idea is you have to sum over all the final states, inclusiveness, to end up cancel those diagrams, then lead to these soft factors. So then if it's a TMD, you have a transverse momentum flow between them. So then means the gauge link from soft fact will not be exactly connected at this interact point, it's -0 with the y per. But if the collinear factorization because integral over transverse momentum, so the gauge link is exactly in the same line column. So when you integrate over the whole thing, unitarity tell you this is exactly equal to 1. So if for the collinear factorization, you only have a PDF, it's a time the hot part, another PDF. But if you do TMD, you will have a soft factor. You have to break the soft, but soft factor in this case is universal. Then you could try to take a square root or whatever, like John Collins did, break it into the definition of the TMD.
Okay, thank you. Thank you very much.
Yeah, if you have a question, let me know. I added those 4 slides for the backup for people who are interested.
Oh, I don't see other raised hands. Alex, Filippo, are there questions from the chat?
There are no questions from the chat.
Okay, then let me remind you as well that not only you can ask a question on Slack, but we will reconvene tomorrow at 4:30 for a recap session with John Wei. This is only for the HAC students, not for the attendees, but HAC students, we will have an optional recap session with John Wei at 4:30 on BlueJeans, where you can ask many more questions. So you are very welcome to think more about these things, and then let's meet again and discuss with John Wei. At this point, we can break, have a 19-minute break, and come back at 2:55 for the 4th lecture.
Okay, thank you guys. See you later.
See you.
Yeah.
Filippo.
What?
One thing, there is also the Hack Social this afternoon. We should let the students know. Make an announcement at the beginning, at the end, maybe, and at the end.
Okay.
And then we can join gather at whatever 4:15 something, or maybe 4:30. We can decide 4:15 maybe, and then people can trickle in. Maybe 4:30.
Yeah. Okay. No problem.
Anyway, it's open, so enter when you want.
Mm-hmm.
John Wei, I see that you are there and active. Can you switch on the camera when you lecture? It's nice to see the lecturer expression. Needs a little bit of feeling, more dimension to what you're talking about. Oh, I see you.
Okay, but the only thing, in case there is a problem with bandwidth, I think because my neighbor all working.
Okay. Well, absolutely. If there is a bandwidth problem, just switch off.
Okay, sure. Then I can keep my camera on. So should I start to share?
Filippo is about share.
So I was waiting 1 minute more to start since
Share looks good.
But
okay,
it's perfect.
Okay. It's getting better now. Once I'm almost done.
Yeah, definitely.
Yeah.
Okay. Polarized beams. Okay.
So I travel, with the full lecture, I cover as much as I can to connect it to the JLab program.
Yeah, no, I noticed also for the future REYES program.
Yeah.
I also see that you put a lot of jet reconstruction, all the work with Kyle and yeah, with jet algorithms and all of that. So pretty interesting.
Yeah, jet, the mini jet algorithm.
Yeah.
So time is so limited.
Yeah, I know. Would be we will need like 3 weeks just for this, basically.
Well, when I gave a lecture for QCD, it's a 1 semester.
No, yeah.
It's a 1 semester course.
Definitely.
Yeah.
It's pretty dense, the material and the and the information presented, let's say. Okay, do you want to start?
Okay.
Okay, so welcome everyone to the last lecture of John's Way's part, the introduction to QCD. And before we start, just some reminders. First of all, I put the material for today's lectures, the link, direct link to that in the chat. So if you want to check, it's there. And after this lecture, we will also reconvene on GatherTown, because if you check on the timetable in the Indico page, you should see that there is the Ag Social. So it's just a social gathering to talk with other students, with the lecture, with the organizers. So please join us on GatherTown at the end of these lectures. And that's it. So John Wei, please go ahead.
Okay, great. Well, thank you everyone to coming back. Then for this last lecture of my 4 lectures, and you can download the slides from website. Now you notice there are lots of backup slides. The backup slides really give you the information on the spinlet, because this lecture I'm going to talk about QCD for cross-section with polarized beam. So you have another degree of freedom, another vector spin involved. So a lot of technique related to that, it's in the backup slides. So I started with a polarization and a spin symmetry. In that case, because I mentioned to you before, you have another knob you can change, can pick a difference of the spin to cancel certain quantity you already know or not greatly interested, but you like to see the quantum difference effect. So the idea is that when you have a cross section, in principle, You have physical cross-section, you have in terms of power expansion, in general leading power, next leading power, and all the powers. But whatever happens, the cross-section is always a positive definite. So then the spin average cross-section often defined as an average over the spin vector. Then they have cross-sections with spin flipped, because the sum is always a positive definite. But however, the symmetry is defined by difference of the two spins. They have a double spin symmetry, both longitudinal polarized, for example, both transverse polarized, or one longitudinal, one transverse polarized. So often the way defined it is according to this combination. Then sometimes you see a much simpler form because there is a relation between different terms due to parity time reversal invariance. And also you can have situation only have one beam polarized. So in that case, we call single spin symmetry. You can have a single symmetry with a longitudinal polarized beam or the transverse polarized beam. If it's a longitudinal polarized beam from a parity, you know that you can only see non-vanished answer with a parity violating observable. If it's a parity conserving, longitudinal polarized beam will not give you a final answer. It should be 0. But transverse polarized beam, even the parity conserving interaction, you still have a non-vanished answer. This is something I will pay attention to explain that. Then when we talk, imagine you have a proton beam. So I want to emphasize there are two rows of the proton spin program, for example. The proton is a composite particle. Spin is, in a sense, is a consequence of internal dynamics of the bound state. So in that case, the decomposition of proton spin in terms of quark, the gluon degree freedom, helps us to understand the dynamics of fundamental QCD bound state. So in the sense that because nucleon is the building block of all hadronic matter, it's very, very interesting. But there is also another part of a proton spin. Suppose that we can use the spin as a tool to help us to select certain symmetry or certain property we want to study. So in this case, you use the spin as a tool. So it's especially related to spin symmetries. So the symmetry can be purely a quantum effect. I'll give you an example later. So then what is a spin? A spin of we all know spin is just an elemental property of an elemental particle, but what is the spin of a composite particles? So the spin was first introduced by Pauli a long time ago, but in a sense, it's a quantum property. You have h bar times this as a quantum values. But the interesting thing for us is really the composite particles. Now, what is the spin of the composite particle? In the sense, it's a total angular momentum of the particle when the particle is at the rest. That's the spin of the, say, proton, because proton is not elemental particle. Same as spin of the nucleus, then also similar issues. So that in the naive quark model we did at the first lectures, then in the sense that it's like a quantum mechanical problem. You have if you know the state, then you know the operator of spin, you sandwich the spin operator between the state, you get the number. So you can imagine you have a SU6 model for the quark. For the proton, then you have it's a wave function, it's a state. Then you have an operator, so in between get a half. So that's exactly how you calculate. But in a quantum field theory, it's different. The quantum mechanics pictures, the number of particles is fixed. No matter how big the system you have, the number of particles is fixed. It's a number. Then, however, in the field theory, the number of particles is never fixed. It's always quantum fluctuating. That's why you will find it eventually when we talk about spin, proton, the quark contribution to proton spin in terms of certain percent. It's a fractional. It's not the say spin half or multiple spin half. It's really the fractional numbers. So that's because number is never fixed in this case. I remember when I first talked to condensed matter colleagues, they say, oh, spin is just a superposition over all the spin of the particle you have. I said, no, because I don't have the number of particles I have at any given time. Then, so the spin of the nucleon in the QCD, in a sense, it's an expectation value of proton waveform, the operator of angular momentum. So that in the field theory, angular momentum operator is defined in terms of energy momentum tensor. They integral over project on this form, you get an angular momentum tensor. Then you, in a quark field, you can have dependent on the quark field and also gluon field. But the problem is, in gauge theory, whenever the particle move, whether it's a quark or gluon, when they move, then you have a covariant derivative rather than normal special derivative. So that's why define the so-called quark spin and the gluon spin not unique, because you always have a covariant derivative in a quark part involving the gluons. So that results into many different definitions. But that's something you should know when you're dealing with gauge theory. So you need to have a matrix element of this kind of operators to define the spin. So people introduced it, the spin sum rule is defined the spin state of the proton with a spin operator in terms of quarks and gluons. So you define that total is a half, you put in the quark part or gluon part. Of course, the separation between them depend on how you treated the covariant derivative. One way to do is say you want each of them be gauge invariant. So then you know that you have to have a covariant derivative, you can have a simple special derivative to make a gauge invariant quantities. So there you have a decomposition, you have a spin of the quark, some of all the flavor, we use delta sigma, there's helicity of the gluon, and the orbiting and momentum part of the quark and the gluon. So those are the proposed decomposition. Now, of course, there is some difference between these two approaches, depending on how you construct, including the delta G. In the Shantung-Giz approach, you don't see this term, the angular momentum of the gluon, including the orbital and all together. You only have JG. But if you define this way, because delta G itself is a measurable quantity, you can imagine the LG is whatever the JG minus delta G. So either way is fine. So after many years of effort, we know so far that delta sigma, which is the total quark contribution to proton spin, is about 30%. And the gluon is about 40% based on the measurement from REYES. And also the last piece, orbit angular momentum, we don't know. We just start to measure because everything is related to transverse motion. So in the sense, if you measure TMD, although it does not directly relate to that, but it gave you some idea on the transverse motion. So this is still open questions, a lot of efforts going on. So then I start with a simple process, like we already started lepton-hadron scattering process, by including the polarizations. So imagine you have a spin, the longitudinal polarized lepton spin and a hadron spin. And in this case, the resolution again is a Q square. Same, we talked before. So H bar is tiny numbers, so you're really dealing with a short distance physics. So if it's a 2 GeV, then it's dealing with the side. Then in inelastic, that often the name X broken I mentioned earlier, that tells you effectively direct measurement of momentum fraction of parton at the lowest order. So if you recall the formula we had from lecture 2, you have this 4 term when I decompose it. So if this W mu mu contracted with the L mu mu give you the cross sections, but there is a 2-term dependent on hadron spin, 2-term does not depend on hadron spin. So if I do the polarized case, you take a symmetry, since this does not depend on spin, so these 2 terms canceled, only the G1, G2 survive, dependent direction of the spin. So that's how you see the structure functions. So when we construct it, then the difference of this hadronic tensor depends on spin flip about 100 degrees. So in the sense, I can introduce the lepton going this way, hadron spin certain directions, then the scatter lepton define the leptonic plane, then the spin gives me another plane, then the angle between I call alpha. So then you can define the helicity is around the direction of the K. So you can see that cross-section, instead of a fixed alpha, that's some number, alpha can be any number you choose. Then in that case, the difference you want to do is to define the symmetry as alpha minus alpha plus pi. So the formula, as you can imagine, we're proportional 2 terms, one is G1, another G2, another one G2, but coefficient depend on the direction of projection of the spin. So that's how we do measure this G1, G2 by measure this difference of a cross section, or divided by sum, do the symmetry, because we know that denominator is a spin average cross section. Then you can, by varying the kinematic variable X broken at the Y and the Q, you can eventually extract the G1, G2. So that's a specific choice you can direct. If you choose alpha equals 0, then you can direct to get a G1, or get some combinations. So then, another thing that I want to demonstrate is connected with experiments. This is something that has been measured by many experiment. So longitudinal polarized spin, then the asymmetry is defined in terms of the difference between the spin flip. In this case, you can either simplify the hadron or lepton, they're equivalent. So they're directly proportional to G1 over F1 if you choose alpha to be 0. And this coefficient function is just purely kinematical functions. So by measuring this asymmetry, in the sense, you can extract the G1. This is existing data from all fixed target experiment from Hermes and also from a select experiment. This is the current data, so you can see a lot of errors. Then what I want to give you a feeling about it, if I go to the EIC, you cover much wider kinematics, and also you will find that the the data point, lots more data point and much higher accuracies. So then the question is, you can measure cross-section. How the cross-section will tell you. So remember, when we do spin average cross-section, you measure the Poisson distribution or transverse momentum dependent distribution, give you some information on confined motion. So here is you do say holistic distribution. That's what you will find it. So imagine this is the formula you are so familiar with now. Then there's a tree diagram. Usually you take the lowest order, spin average one is just the sum of the quark distribution. But when you take a difference, actually we call holistic distribution. I'm going to define in a moment. So G1 is like F1 is actual proportional delta Q or delta Q bar. Then also the function, if you put the charge into it, this is also related to the different part of a holistic distribution. The definition of delta is in the sense you have a quark, have a holistic around the direction proton spin minus quark probability to find a quark with its holistic opposite to the proton spin. So that's the physical meaning. So you can see, but in general in the formula, if I decompose this photon hadron scattering amplitude, imagine this is the part I talk about script H part versus the matrix element part. I had IJ in my previous transparency that represent the polarization state of the spin vectors, or gamma mu mu is the index of gamma mu mu. Then you can contract it. What we had before is a gamma plus contraction that give you the polarized distributions. Actually, you can have different contractions of these, give you the different spin state for these two quarks. But you know, if you have a spin half particle here, spin half particle here, how many different independent projections, spin projections you have? Answer is a total of 4. No matter what you choose, you never change your degree of freedom, right? Each spin has a 2 state, and a 4 state that corresponding to a spin average one, and a history distribution we talk about now, and also I may not have time to cover this so-called transverse distribution, which depend on another 2 degree freedom. You have 4 total degree freedom for the quark helicity or quark spin distributions. So then in terms of decomposition, you can see that's the distribution in general. Into there, it have spin indices, so I can decompose into gamma matrices. So you will find it, as I just mentioned, that only 3 types will survive. If for the massless case, you have a single gamma term, then the gamma with gamma 5 term, and the 2 gamma term, which is actually time reversal. This chiarity R. So it's related to sigma mu mu term in a matrix number. Then, so that's related to transverse distribution. This is holistic distributions. Then that's projection, exactly the spin average distribution, the gamma plus, and this gamma 5, the holistic distribution. This is known as transverse distributions. So those are the things you can hope to extract from the measurement, the cross sections. So then in terms of definition, like what I showed you before, I put in the more intuitive way in terms of probability. So imagine this spin average cross section corresponding to you produce, say, electron in the helicity, then the square, then minus these things with the minus helicity minus square. Then this should be a minus sign. Sorry, I forgot. Then this way, the helicity is difference. Then this is a transverse, the S per. Then, so that's how the intuitions. Then there is a more systematic tool. This is something, if you're interested in the theory of it, it's a very, very powerful tool, because what happens when you change, you want to isolate something related to spin. Well, always think about time reversal invariance and time parity transformation. When you have a combination of a parity and time reversal transformation, you will keep the linear momentum intact, but the spin flip the sign. So in general, whenever you're dealing with a cross-section, meaning an operator, depending on quark field and gluon field, sandwiched between the hadron state with a spin S. So then I take a simple case like a quark distribution is a sidebar with some gamma matrices reside. That's a quark case. But in general, it's just an operator. So when you apply the parity time reversal invariance, you can prove in the back of the slide is that the matrix of that operator is equal to the matrix with the spin flipped, but the operator is contracted by the application of the time reversal and parity transformations. So then you can see that the so-called, if the operator is a good operator, whatever the operator, like a quark operator, and the P and the T, if you just change the plus minus sign, those are so-called good operator, and the P and T, you get the eigenvalue is a +1 -1. If that's the situation, if this is the situation, then immediately you can define if the +1 will contribute to spin average cross-section, -1 will contribute to spin symmetries. That's exactly how the symmetry is defined. So immediately as a homework exercise, this is the operator you know. For the quark, you have gamma plus, gamma phi, sigma mu mu term, or for the gluon, the F plus alpha with it's contracted. If you contract it with the antisymmetric tensor, that's good to delta G. If you contract it with G mu mu, G alpha beta, transport by G alpha beta, you get a normal spin average gluon distributions. But for others, you give you different either spin averages, helicity distribution, or transverse distributions. So these parity time reversal invariants are very, very powerful whenever you're dealing with a spin. So I left a lot of notes or the slides in the back of the slides that give you a lot of information about these, how to apply this, study the spin physics. So with those in hand, so now you can do the measurement. That's what the EMC collaboration measured in 1987. So they find that G1P, we integral over that, then with combination with decompose this delta U, delta D, you can from difference, and also this the other measurement can be from this parity beta decay or other measurement to get this information. From the bottom line is that by measuring these quantity integral all the moment diffraction, they can extract the delta sigma. So that time that we know delta sigma as defined is total quark helicity contribution to the proton spin. So what they find is at that time in 1987, the delta sigma is consistent to 0 with a large error bar, of course. Then, so that's create a lot of activity, so-called proton spin crisis, because before that time, from quark model, as we just went through from this lecture series, then proton spin completely given by the quark. If you have this SU6 wave function for the proton, the spin half will all come from the quark spin. But in the real life, they extracted from at whatever scale you probed it, you find the quark contributed almost 0% to the proton spin. So by now, after all these years of refinement, as I showed you earlier, quark only contribute probably about 30% of the proton spin. So the question is, we understand better now, it's not the real spin crisis because the gluon and the motion, they all contribute to proton spin, but instead of the crisis, we really enter the new era of spin physics, try to understand internal dynamics of the proton, how the proton spin was formed. So I told you before the physical cross-section, if the Lorentz event not depend on the frame, but sometimes the intuition or the physical picture to penetrate the frame. So I mentioned earlier last lectures, in response to a question. So imagine you have a proton in the restaurant, then you boost it very, very fast. You know what happened in the proton waveform? Imagine a valence quark, a lot of quantum fluctuation around it. So when you boost it, it's a time dilation. So imagine this time for this gluon fluctuation could maybe very, very short time, but when you boost it so fast, the time can be sufficiently long. Compared to the long, always relative compared to the probe. Imagine I have a probe, the time the 1 over Q is so much smaller than considering that the long time is the quantum fluctuation, I can see the quantum fluctuation of the proton, the quarks and gluons. Because if the momentum is large enough, I can define momentum fraction. So that's exactly the picture. You can imagine how this can take place, but whatever the quantity you calculate, the cross-section should not depend on the frame. Then the PDF Polynomial distribution itself does not depend on frame either. So the question, what does the spin relate to the probe? So far, I gave a couple of examples. One is that when you have a lepton or hadron collision, like a JLab or EIC, or Europe, where you have a compass, you can have a polarized lepton beam and polarized hadron beam. Or you can have, don't measure anything, you sum over everything in the final state, like inclusive, then measurement. So in that case, you can measure helicity distribution, or do the semi-inclusive, measure pion or kaon or jet in the final state, like a JLab or EIC. So in that case, you have a situation to study the spin dependence. At the same time, you have an extra probe from a final state to adjust the kinematics. Or you can hadron-hadron collision, both the polarized, or as well as the exclusive process. So there are many possible processes. But with the hadron-hadron case, because Brookhaven has a special spin program with both proton being polarized, they collide. So you can take advantage of the single spin symmetry with the one proton is polarized, other protons being averaged. As we know that if you do that, you realize if it's a parity conserving thing, you end up with a 0. But if you look for the observable, which violates the parity, you actually get a non-zero symmetry. From that, you directly test something related to the this sort of weak interaction, in this case, look for W's. So they can measure W's, then also because W is left-handed in this case, then you will find that from the measurement, local W plus is dominated by this combination of the lowest order, the delta U bar, if this side is polarized, then you will find it is 1, x2, the momentum fraction, because if you measure W with its mass and the rapidity, you can uniquely, there's a mass and the rapidity, you can fix x1 as 2 at the lowest order. So imagine you choose your kinematics in such a way that rapidity is going in the one direction, then you will find it's a more favor to the ratio of delta U over U if you look at the forward of W plus. Now, if you look backward for W plus, in that case, you will find a more favor to the delta D bar over D bar. So you can see, take advantage of these, you can have a much better sensitivity on the polarized, the helicity distributions. Then, but of course, when you go to higher order, things get a little bit more complicated because of convolution. I just give examples to show you what EIC can do compared to what we know now. From RIC measurement, from a delta G, gluon polarization, which is very important, it tells you how much contribution to the proton spin, and because the quark contribute only about 30%. Then the so far range of momentum fraction is very limited from the RIC measurement. But imagine you can expand it, say, from a very low to have certain uncertainty. You can see push just from 0.05 to 0.001, then the uncertainty of delta G is huge. But when you go to the EIC, because of expanded kinematic coverage and much better luminosities, you will find the delta G with the Q-squared of 10 GeV uncertainty can be so much smaller, all the way down to 10 to the minus 4. The light blue is a current uncertainty. Then this medium blue is with the 45 GeV. That if you go to high energy, push to even smaller X region, the dark blue, you can see how much control you can have in terms of uncertainties. Then similarly for delta sigma, we know we already do a pretty good job from a light blue for this region, but if you go to EIC, you can make them even better. So with this good control, even though we know now exactly where the central value is, you know how much room you left for the orbiting momentums. So you will find that if this is a side of uncertainty, then for the L is more or less close to 0 or have a little bit of room for the orbital angle momentum. So whether they have orbital angle momentum or without orbital angle momentum, will have very, very important physics consequences. So that's a double spin symmetry. Then that's a very interesting thing is single spin symmetry. I mentioned it earlier. Then if you do the experiment with only one particle is transverse polarized, then initially, it's more than 40 years ago now. It's 45 years ago. No, then even longer. I'm sorry. This I picked the wrong number. I didn't think about it. Then Norman, Chris, and TTD from Columbia made a proposal. Then they say under the time reversal invariance, if you polarize the transversely of the hadron proton, do the lepton without polarization, you can average over the lepton spin. That means a symmetry measure only single spin. So define this way. Then they predict in the approximation of a one photon exchange, that A sub n, the symmetry, including S, should vanish if time reversal is invariant for electromagnetic and strong interactions. That prediction was tested by precise measurement by many groups later in the 70s. Then they find it is consistent to 0, but it's slightly different from 0 that can be attributed to the two photon exchange. So they did a very interesting prediction. So here with your knowledge and knowledge from this lecture and your class, then you can easily prove it in one slide effectively, because take advantage of parity time reversal invariance. You know, the cross section, as we discussed, is the leptonic part, which is unpolarized, multiply hadronic part depends on spin. So leptonic part is symmetric, it's unpolarized. So hadronic part is proportional to current correlator sandwiched between the proton state. So the asymmetry is a proportional difference of two this hadronic tensor with a spin flip, because the lepton part is symmetric. So the question is, A sub n equal to 0 means whether or not the matrix element, this guy equal to the one with a spin flip, then attachment. So they can test it. So you apply time reversal. Now you can define the quantum state when the single state proton state. Another one, you can imagine the state with the two currents. So you can apply the T reversal on that, the T change both P and S. Then the beta, of course, you reverse, you change the state, you have to have a complex conjugate because time reversal transformation is not unitary. So you immediately derive this form. Then you can see that the time reversed state immunal product then should be related to this V DAC of the V. So then it's related to the one because the complex number time reversal. So with the one without reverse. So immediately from this expression, plug into here, then you will find you derive that this matrix sign with the flipped state is related to equal to this one. You plug into that. So this is the matrix element. You put in the unitary the parity part. You work a few steps that immediately proved with the operator with the spin flip is related to the matrix element operator with spin flip. Is related to the matrix operator without spin flip, but the Lorentz indices switch. They're equal. So now if you plug into the expression, then put it into here, then immediately you'll find this is had to be the opposite, then you plug in, it's 0. So that's a very quick. You can prove for inclusive case. Then also here, there is experiment evidence from hadronic case. So what this measurement is, you have a proton-proton scattering. Look for the final state pion. You look for the proton has a spin direction. You have a collision momentum with spin direction define a plane, right? Spin the transverse price, beam coming, hit each other, then you can define a vertical plane. But you will find that the particle come out of the collision in the left-hand side plane and the right-hand side plane, not symmetric in the pure strong interaction. Ever since low energy from Argon experiment, all the way Brookhaven experiment, Fermilab experiment, you will find a symmetry actually pretty big. That can be 30% to 40%. Then as a function of XF, the XF is the longitudinal momentum over the half root S. That's so that in the hadronic case, it's a single spin. Then there's no parity violation. Then what happens? So then people even push the the spin program goes to the much higher energy. Then we find again large spin symmetry, although the absolute value of spin symmetry is small, but still there. So then the picture I show you, the collision axis, the spin axis define left hand, right hand of the plane. Then you will find the particle coming out to one side, it's not the same as the particle coming out the other side. So then from physics theorists, because that was in the early 70s, so the physicist theorists immediately jump on it. So, okay, how can I generate in the QCD? This is by John Pumplin, Goldie Ken, John Pumplin, and Wayne Rapko from Michigan. They have a paper in 1978. They say that if you have a scattering, imagine you have a proton from this side, from a hadron, you have a tree diagram scattering, but you can, because of the time reversal, you need a phase, otherwise it's 0. So you have to have a loop diagram. So they have a loop diagram to give you a phase. So it's a difference to give you interference. Then you will find this calculation because if it's a massless, it's a vector interaction QCD cannot flip the spin. So in order to do that, you have to have a mass term. So the asymmetry, according to that calculation, is very reasonable, had to proportional of S times the mass of quark of a transverse momentum of hadron you observe. Of course, the mass of a light quark is almost 0, so then this asymmetry had to be 0 in the asymptotic limit. Then, so this is the root of the problem. There has been a debate for many years between theory and experiment. Then how can you generate a single spin even in the asymptotic behavior, the QCD in the asymptotic region? So in this case, then what do we need to generate spin in terms of the vector you have? You have spin vector, and you have a particle you observed, the incoming collision particle and the observed particle. You can construct a scalar. That's a symmetry of the cross section. It's a scalar. Then you realize that scalar S dot P cross P is time reversal art. So whatever you construct for a symmetry, you have to have a phase I. So then if you put in the full vector form, the Lorentz scalar form, then you have a two beam there, even though they against each other, but they are, the Z component have the opposite direction. So you can have a Lorentz scalar in the full vector form. You can have it in principle, but you have to have a phase. So it's then if the hadron does not, and also you find you have to have transverse direct whatever you produce have to have a transverse momentum, because this antisymmetric tensor, P and a P prime in the same direction, and in the opposite direction, they saturate 0 component, Z component. You ought to have this non-vanish if the spin takes another component. So this guy had to be in the transverse direction with not parallel to the P. That's why you have a left-right asymmetry. So that's exactly consistent from the minimum requirement from theory. So now we understand what's the current understanding for this transverse single spin symmetries is that if you do the inclusive cross-section, if you don't measure final state, you immediately realize that from a photon hadron scattering, you do not even have enough vector, like I just constructed. You need a full vector, independent vector, to construct a Lorentz scalar. So if you imagine the photon hadron scattering, you don't have, if you don't observe anything else, don't even have enough vector constructed. That's one simple way. But also parity time reversal inverse also show you that has to be 0. Then also you have this one scale observable. If you imagine you observe the final state particle, now you have enough vector to construct that. So there are two situations. One is that what if the PT is order of Q? It's a single scale part. It's like the completely asymptotic region, just like what the case studied by Goody-Can, John Poplin, and the Wayne Replico, many years ago. So in that case, the answer, can you generate spin symmetries? And another situation, if the PT compared to that is not a small change, it's a TMD form. So you have both initial state, final state interactions. In the Joyang case, hadron case, you can generate some spin. And also you can have this single scale. The 2-scale problem, when this PT is so much smaller than Q, then the TMD form, you can generate spin. So what in terms of QCD factorization, in this case, it's a purely collinear, it's a single scale. So it's a collinear factorization. The early work down showed the 0 because leading twist is 0. So in the sense that George Sturm and I actually proved factorization theory, you can get a non-vanish answer directed at the twist 3 level. And we can explain why you can flip a spin even at the twist 3 level. Then if you do TMD, you can have to have a different factorization, TMD factorization, then you will have the non-vanishing symmetries. So collinear factorization actually, in the sense, you integral for transverse momentum. In the average sense, you get a symmetry. So those are general understanding. So now I give you an example. So how can you generate in the collinear factorization? Imagine the diagram you had. You have a hard collision, a parton coming without polarization this side of the hadron, have a really hard collision, produce something with a large PT, order of Q. Then you can have a situation in the quantum theory, some of all the possible amplitude have same initial state and same final state, then square. Then you will realize that you have a situation of one active parton, like we just did, normal situation. If the cross section, you have a leading twist distribution from this side, leading twist distribution from that side with a hopper. But also you can have a situation, you have a core-gluon composite state from one side. They're collinear. The transverse momentum integrate over. But you produce that, but you pay a penalty by pulling these two things together, you pay a penalty on 1 over half scale. But your proportional distribution is, in this case, it's not the square of this one, it's this one interferes with that one. So it's a 3 line, so you 1 over Q. But does not have a probability interpretation because amplitude have a single parton, the complex conjugate will have 2 parton composite state. We call F3, twist 3 distributions. Then you can continue on have power expansions. Now the question is why, if you take a difference of the spin asymmetry, you will find the first term does not depend on spin, they cancel. First term directly proportional single spin asymmetry, in the sense you proportion the matrix element known as twist 3 distributions, one side the single active parton, other the composite active parton. This exactly explains why you can flip a spin. Single spin asymmetry means that active parton, this side, and the state, this side have different spins direction they flip. Then QCD is the vector interaction. This quark can never flip helicity, the same as this guy. So what happens is a composite state gluon can have a spin 1 in the opposite direction. If the quark spin half to go in this direction, gluon spin can be in that direction, the composite state can be minus half, that this amplitude and that amplitude will have effectively flip a spin. Same for a fantation picture. That's the exact reason you can, this measurement asymmetry directly test the quantum interference in the QCD level. So then what's the corresponding to operator for twist 3? The twist 2 operator, we already know the type, there's a spin averaging one for quarks, gluon, and delta G, delta Q, delta G. The transverse state require the chirality off, so I'm not including them here. What's the twist 3? It's done by Zhongbo Khan myself. Then we find all the possible operator consisting of the closed set is exactly the same operator, sandwich additional operator related to Lorentz force, is a magnetic force. So that defines the twist 3 distributions. Then that's exactly, if you think about quantum mechanics pictures, the wave function in the relativity is like the feel like a wave function, relativity wave function. Then you have operator. So single spin symmetry in the sense of expectation value of this transverse force inside the hadrons. So then so the picture here is that, as I mentioned earlier, is the really composite state interfere with the single parton state, applies to both gluon case as well as core gluon case. So the operator, you will find this term is nothing but color Lorentz force. I can even give you a more intuitive model, give you the feeling, how can you generate this kind of single spin symmetry inside the composite state? Imagine you have a particle come in as a probe with the momentum hit a composite state. The internal particle can have some motion. So the collision, because it's a momentum change of this particle, is equal to Lorentz force, V cross the B. Then you will write it into the sort of more Lorentz invariant form in terms of field strength. Then you will write in this form. If you put in the momentum in this form boosted into like called momentum, this operator is the exact same operator I showed earlier on the general definition of twist distributions. So the physics there is a Lorentz force in the bound state. They control or correlate with the motion of the partons. So the motion of parton inside a polarized hadron has a certain preference. So then of course, like a D-Glab evolution, this twist 3, if it's factorizable, you must have evolution equation associated that. So we derive the complete set evolution equation for these, then of course a little bit more complicated than the normal D-Glab distributions. If anyone interested, you can look at it. But here I gave you just a couple of examples. Remember now it's a 3-parton state. So you have a projection operator define your twist 3 distributions. Then you have a projection operator when you project on the parton state. So this is a corresponding operator. Then eventually give you some feeling about the how part you can derive. It's similar to what you normally derive for the twist 2 case, but just a little bit more complicated. But interesting is give you a new physics. Corresponding correlation, quarks, gluons, rather than probability. This does not have probability interpretation. Okay, so that's for a single scale. That means you don't have transverse momentum. In a sense, transverse momentum, the integrator over. So whatever symmetry you find is in a sense relate to the moment of the transverse momentum of the parton inside a polarized hadron, which is the consequence of that the spin of the hadron corresponding to the parton's motion have certain preference. If you integrate over the moment, that means moment is not equal to 0. That's why you get a twist 3 distributions. What if you have an observable can direct to be sensitive to the moment itself, to not the moment, the motion itself, to the PT? That has to be a TMD factorization. That means you have to have a 2-scale observable. I go back to same semi-inclusive DIS. You have electron scattered with the hadron, look for electron. But now, in addition to the scattered electron, you look for the hadron in final state. If you do that, then you will find you will have a leptonic plane and a hadronic plane plus whatever spin vectors. So in that case, I can always choose the frame of the direction photon and the hadron. So this is my z-axis. So if you produce for momentum conservation, you know the parton coming, hit to the virtual photon. People often use words like a brick wall, like a bright frame. Photon acting like a wall because a parton coming hit to the photon going backwards. Because momentum conservation, the only way they can go back. Then, so in that case, if the parton coming has a little bit tiny transverse momentum, because the confined motion in the proton wave functions, the parton bounce back have to have a small transverse momentum. If that parton hadronized into a pion, for example, the hadron in the final state, that the transverse momentum of the pion or the final state particle should have a small transverse momentum in the frame photon hadron frame. So whenever we talk about transverse momentum, you have to specify frame. So if you do so, that means you have two hadron, as we talked before, then if the two hadron are, if the PT is small, then you have two scale problem. What if you can, have a PT, but also radiate another parton in the final state from a higher order, you can still have situation, even in that frame, PT can be large of the Q. In that case, a scale, again, in that frame, it's a single scale problem, so then you can apply the so-called collinear factorization formulas. So that's not what we interested here. Here interested is a two-scale problem. Because when the as I mentioned before, to prove the factorization, it's difficult. Most difficult part is soft gluons. Because in this case, imagine the picture I had earlier, a photon, a quark coming from the proton, hit the photon, produce a scattered quark, eventually hadronize into the observed pion. Then from our early discussion, we know all the quantum difference between this part and the hard collision is suppressed because typical momentum scale here is order lambda QCD. Typical momentum scale in the hard part of the Q, so it's power suppressed. But most difficult part, the proof factorization, is a soft term, meaning the interaction between these two soft hadrons, meaning the parton distribution from initial state, fragmentation function from final state. In the Joy-Yang case, is a soft interaction between two hadron, initial state hadron. So semi-inclusive DIS actually is between the initial state hadron and the final state hadronization process. So again, similar to the proved Joy-Yang cross-section, if you go through those 4 slides given to you, you should be easily understood. This can be factorized, the collinear distribution around the direction of the hadron observed, collinear distribution, those are gauge link, relate to hadron coming, then rest of the soft factor, because the transverse momentum flows, so soft factor is not equal to 1, so you have some false factors. So factors theory in this for semi-inclusive is well defined. The low PT region in the photon hadron frame, you have TMD factorization, so distribution depend on PT. Then when the high PT region is a collinear factorization because it's a single scale, the correction term. And even if you integrate over PT, it becomes a single scale, it can be factorized to the distribution of fragmentation functions. Then even, I didn't include a situation, what if I situation, the Q squared is not too big, but the transverse momentum is still big, then that's another situation. Then in that case, a different factorization formulas. So the theory is solid, what I try to say. So then what kind of transverse momentum distribution you have? If you imagine you have a proton, have a spin. If you probe the quark not only can have a momentum, but also quark have different spin state. I told you earlier, the quark is itself a spin half, but a correlator between quark, you can have 4 spin states, because 2 half give you the 4 spin states, so you can have either spin average or spin dependent helicity or transversity operators. So in a sense, you can define the correlation between the hadron spin direction and the parton spin direction. So at the end of the day, you can say this line corresponding quark spin is an unpolarized quark spin operator, longitudinal polarized spin operator, or transverse. The same for the hadron spin. Now you will find it that if for the collinear factorization, you have a 4 state. I told you there is a spin average distribution, spin helicity distribution, and the transverse distributions. But once you gave the transverse momentum, you have additional vectors. From that additional vector, you can construct additional scalar functions. But not every possible scalar function finite because of parity time reversal invariance. So we'll find that at the end of the day, I leave it to you as something to think about it, but you can literally prove through every single step, there are only 8 finite non-vanish TMDs for quark within the parity time reversal invariance. And so that's exactly, so some corner vanish, you can easily find a reason why they vanish. But the question is, if you measure this correlation function, that gives you the information how the quark is correlated with the gluons, or quark correlated with a global property like spin. Quark is a spin, quark is a motion, correlated with hadron spin. But when you do the asymmetry measurement, sometimes you could not distinguish them. I give you an example, say, I look for a pion in the final state. My proton is transverse polarized, so I know the certain parton flavor have a preference in the motion. So whatever I produce, a pi and plus, pi minus has preferences, maybe a little bit more on this side. But this is not the only channel I can produce that. Imagine a situation I can have produce a so-called transverse distributions. Then you have a transverse provide the quark you produce, but the quark have to hadronization. Because the quark have preferred the spin direction, hadronization process have also introduced spin direction. So as far as what you observe, since you never see the quark in isolation, what you see is just enhancement of the quark hadron produced on the one side. So symmetrical could come from this approach or come from this sub-process. How to distinguish them? That's hard. Well, however, lepton hadron scattering is unique. Semi-cool DIS, I emphasize, is the best for the probing the TMDs. Because you naturally have the two planes, leptonic plane and hadronic plane. Now you can define the angle between the plane and the plane, between the plane and the spin vectors. Now you can construct the measurement, which of course depend on those planes. Now you will find that you can have different angle modulation of those angle distributions. You will find a different asymmetry contribution to the symmetry, like a Sivers type effect or Collins type effect. They're corresponding to different spin exchange. They actually correspond to different modulation. So you realize that if you do the spin symmetry in that case, then a single spin symmetry that has 3 terms. Then one is proportional more like a Collins type I mentioned due to the hadronization. One is a Sivers type due to the motion of the proton in the polarized hadron, and the Petrovarsky is due to the interference. So, but they have a different combination of the angle. So if you, from data to different modulation integral of that, you can directly extract those functions. But if you do hadronic collision, it will be very, very difficult to separate them. So lepton hadron scattering is very, very good for the detecting that. Then that's for the transverse motion. Another thing I want to touch up because you're here, you already heard lecture this morning about the DVCS or try to understand the 3D images. The idea is very simple. You can probe is so localized, hard scale, but they're also sensitive soft scale. You can look for transverse motion, end up with TMD. But you can do the diffractive scattering. So the momentum in of the hadron is slightly different from that. You have a T exchange. By Fourier transform the T exchange exactly actually give you the transverse position distributions. That's not give you the 3-dimensional images. So then because the proton is not like point like we know that. But there is a one big question we like to ask. Then we know how to find a charge distribution inside the proton. We can define the radius by measuring the elastic form factors. So the one obvious question people say, how the color is distributed inside the proton. We know the color is quantum fluctuated is like a brown mud. But if there is any structures, well, answer is you cannot really never can really directly probe that because you never have elastic form factor because by exchanging by gluon, you can exchange the photon because the photon does not carry charge. But if you exchange the gluon to define the form factor, then the proton cannot stay as a proton. So there is no color elastic form factors. So what we can measure is really the density. So we try to understand the density distribution, the density of quark distribution inside proton, a density of gluon distribution inside proton. I give you an example of say, how can you probe the density of the gluon inside proton? What did that tell me? Imagine a photon scattering of the proton to the diffractive of the proton, have T exchanger lowest order, and produce J psi, have larger momentum. But you say, well, wait a minute, you exchange a vacuum quantum number because proton to proton is a vacuum quantum number, even though momentum is slightly different. If you exchange a vacuum quantum number, you don't have to be just 2 gluons, you can have any number of gluons. They contribute. But theoretically, you can prove, as I mentioned earlier, then because the larger momentum strength, this part is so localized. Only thing gave the leading power contribution, this gluon has to be longitudinally polarized in parallel, so it's gauge link. If the gluon is transverse polarized to connect it to that, because it is that transverse polarization, you pick up an extra power of the hard scale suppressed. So if you go to sufficient high Q square and a larger value mass, you will find that it's dominated by 2 gluon exchange. So you can measure that cross-section, factorize the distribution, this with the 2 gluon, known as a generalized Poisson distributions. Then what you really measure, you never measure distribution, you measure the cross-section as a function of the transversal momentum. So you can do the Fourier transform that eventually you get the distribution of this generalized Poisson distribution as a function of the position space BT conjugate to the T. So that tells you, you can define, for example, it's for different variable X, you may have different shape. When the X is large, a proton has to be localized. But then now you can pose a very interesting theoretical questions, which is a direct impact from the QCD dynamics. You want to ask how fast this distribution fall. That would determine what the nature of the nuclear force. And also not only how fast the fall or how wide how long the tail can be. Those are exactly concept of color confinement. So we don't know how to prove them, that if the experiment can give us a hint, we can help us to understand better. And also from that, once you know the distribution of the density of a gluon and the quark, then you can define the proton radius. So far, proton radius only defined in terms of electromagnetic charge. You can define the proton radius of the quark and proton radius of the gluon density or quark density. Then very interesting question is which one is bigger, which one is small? What's the relation between them? That's exactly tells you the physics behind the QCD physics. And also orbital motion, as I say, there's no unique definition because anything related to motion relate to the gauge invariant, relate to the covariant derivative. That means there is a gluon involved. There are different decompositions. The Jeff Manahan definition uses normal derivative, Shandongji definition with the covariant derivative. But the interesting here is that it's not how they define, the interest is what the difference. Difference is due to that gluon. Remember I mentioned to you that the gluon plays a very important role. This color Lorentz force inside proton really control the motion of the quarks inside the bound state. So difference you can either relate to the operator, that operator is very familiar to you, is exactly a torque, because the actual Y, you can imagine what's orbital angular momentum. Orbital angular momentum is a force acting on has a transverse position, so it's a torque. But it's in this case, just like a twist-3 distribution, it's also like a side by side with the operator. It's a quantum expectation value of this, integral over the whole space of the proton. So that's something you can learn from the measurement. Then finally, people often put the more general, say, if I only thing I care is a pinch singularity, that means these partons are on shell. They don't have to be collinear. And a hadron can be diffractive. They don't have to be around the same direction. In this general case, because the factorization requires the parton to be on shell, almost on shell, by pinch singularity. So most general distribution can define is known as generalized TMDs. TMD say this has transverse momentum. Generalized means you can have a hadron momentum to be different. So that can be related to so-called Wigner functions by integral over part of it. And they also relate to the distributions. So this connection you can find. So that then you can, once you have an operator, you can also try to calculate the lattice. So far, lattice cannot calculate the disconnected diagram, but at least they show the consistency. They find the angular momentum contribution and the orbital angular momentum contributions. Then depending on how you decompose it, you add up to the 100%, but you have a different decomposition, give you a different contribution. Then this is the lattice, lattice has a connected diagram, a disconnected diagram. I'm not going to, because time, I'm not going to get involved. I just give you the reference. Now you can look into interested, we can talk and the recap session if you have questions. So finally, let me summarize for my 4 lectures. I say the QCD has been extremely successful in interpreting and predicting high energy experiment data. When the momentum transfers are larger than 2 GeV, that means the distance scale is less than 1/10 of Fermi. That I show you the data from L3C with the QCD factorization and the QED calculation. We find that cross-section can be different up to the 15 order of magnitude. You can have a consistent one-set parton distribution functions with chi-square between the experiment data and the theory of prediction to be order of 1. But we still don't know much about the hadron structures, the emerging phenomena of QCD itself. And also we don't know much about how the hadron is emerging coming from the produced partons. So there is a new term I mentioned to you on the day 1, the nuclear photography is describe the physics at the Fermi scales. requires a 2-scale probe, because if you have a hard scale, you're not sensitive to detail of the structure. So in order to see the structure, you have to have a 2-scale observable. But the problem is that quarks gluons are confined. You never see them in isolation. So you have to have factorization to link them together with the controllable uncertainties. In the last 20 years, as a major advance has been achieved, both in the experiment size in the measurement, they can measure 2-scale problem, observable, and the theory size, the factorization. So that's a great advantage as gives the solid support, a reason for people to construct this new machine over $2 billion, the EIC, because we'll be able to deal with the 2-scale problem. And also emphasize the lepton-hadron facility is ideal for 2-scale problem, because you have a unique leptonic plane, hadronic plane to the semi-cool DIS. You can isolate, separate the different TMD distribution, which give you the different information in terms of how the quark motion or spin correlate with the hadronic spin vectors. TMD and the GPD are only two. They're also correlation functions. They are accessible by high energy scattering with a polarized beam. They encode very important information on the hadron 3D structures, distribution, as well as the motion of the quarks gluons. I hope this summary is something you agree. And you, in the rest of the school, I'm sure you will learn a lot of detail about these. And I'd like to thank you for attending this 4-hour lectures. If you have a question, please feel free to ask. And we have another recap session. I will try to answer your questions more with more time. Thank you.
Thank you very much, Jianwei. It was really interesting to see the evolution of our knowledge of the nucleon structure, and to see also what is going to happen in the future. They discovered a lot, and we will have still to discover a lot in the future. So if anyone has a question, I'm sure. Oh, I see Daniel for now. So please, Daniel, go ahead.
Yes, thank you very much for this lecture series. I just wanted to know if you could comment briefly on, for these TMDs, how much work is left to do in gathering data and also in describing theoretically how these TMDs behave in the Q-squared and F.
Very good question. Very good questions. Then there are lots of work that need to be done. I can tell you.
Exactly.
Pattern distribution, which is single hot scale observable, took us 40 years. Finally, we have enough observable, enough range of phase space to pin down the distribution that gave us confidence to discover the Higgs particle, discover the other particle, and hopefully we can find anything new beyond standard models. But with additional degree freedom, the TMD have many more functions. We can try to find a new observable to identify how the function can be extracted. Recently, that experimentally tried to see how can I measure this kind of 2-scale problem more accurately. And the problem is a theory. How can I have a formalism can uniquely or precisely extract information you wanted? It's a long way to go. In the US, there is a special nuclear theory. They have this special grant called topical collaboration. The idea is every 5 years, with a call, they give a 3 or 4 grant, lasts for the 5 years. Then you're supposed to solve one specific problem. 5 years ago, they had a call. And one of the major problems is a TMD. We try to understand the TMD. Another major one is the so-called beam energy scan to study the critical point for the early universe, the heavy ion things. Then another, the fundamental symmetries. Then, so actually, I was the PI. I put together the team for the TMD collaborations. We are close to, because of COVID, we not quite finished within 5 years, but there's a 1 year no cost extension. And by early spring next year, we're supposed to complete our project. One of the important things we produce, besides the global fit, like other collaboration, we will produce a TMD handbook, which will summarize all the theory advances so far connected with the phenomenology as well, and the lattice efforts. I told you there's the lattice calculations. Then we started to think about 200 pages, but now already 360 pages. Then the idea is that a lot of development number of years, but a lot of confusions. So the goal for us, really try to have a clear pictures. We are not discriminating anyone. The different approach, we find all the connection between approaches and a pro and a con in our opinion. But eventually, then this thing is not carved in the stone. Then we will improve. Then we will have the summer school. We had one before, but we have another one this winter at Santa Fe. Try to use this as a textbook. Then the student can learn. Then hopefully this will be important for the future studies. And so, as I say, the TMD, there are lots of uncertainties. There's still, we can talk in detail, hours, what the challenging issues.
Cool, thank you very much. Seems like there's a lot of work to do, but also maybe some job security in the sense of
exciting, right? Every
time we're not running out of physics to do.
Yeah, the topical collaboration, one of the requirements is create 2 faculty positions. So we created 2, then there's other collaboration do the same. So next call for topical collaboration, although it has not announced officially, but unofficially we already learned. And also the Tim Holman already said in the NSAC meeting that the end of this year, calendar year, or beginning of next fiscal year, it's the end of this year, calendar years, there will be another call for next round. So then, this kind of the focused object collaboration is very, very important, help us solve the problem. Then there will be later that I mentioned each collaboration at least to create 2 faculty positions, right?
Cool.
Okay. And if you can add something to what Jianwei just said, we also recently published a yellow report on the EIC program, and that's also a 900 pages of future programs, physics, and there is really a lot of stuff still to do and to discover. So, yeah. And the next question is from Matteo, actually, Matteo Cerutti. Please.
Okay. Thank you, Jianwei, for this lecture series. They were very interesting. I would ask you if you can comment something about the limits of the applicability of the TMD factorization. In the world, there is still discussion about this limit Q, very much larger with respect to PhD or whatever else. Can you comment this?
Oh, absolutely. I think there is a misconception in the community. It's unfortunately, but theoretical formula we derive for TMD, we say QT much less than Q because we threw away the term Q squared, not QT over Q. That limit, it's not clear. It's like we don't know exactly where it is. So the idea is that what experiment measure? Experiment measure the PT distribution of the particle in a given frame, suppose in the photon hadron frame. So if you have radio crashing, you don't even have the photon hadron frame fixed. But suppose you do, then you have a PT. But that's what the experiment measure. So they should measure PT distribution pi from almost 0 to whatever the large value is. Then theorists should derive the formula low PT, you have a TMD formula, but a PT order Q, you have a fixed order calculations. Then between is the matching. That has been discussed in the original paper by Collins Soper-Sturman as my paper in the 2000. Then there are many papers. So it's not the focus narrowly on the so-called where's the TMD, because there is no sharp boundary between. So you derive the nice formulas for the whole PT spectrum, including the low PT TMD resummation, TMD formula, which is effectively like a resummation formula. Then the high PT. Now you have a nice match. You could discuss what the best way to do the matching. Now you compare with data. Data experiment should not cut off this, cut off that. You do measure a nice PT spectrum if you can. Then we compare them to global analysis. We now the computer is so much faster, and also we develop a much better idea to do the global analysis. So we have extracted both collinear distribution as well as the TMD distributions in the global analysis. In this case, you will not artificially cut off certain things. Just like in an early TDF case, we say we throw the power correction. Nobody says we have to be accused of 2 GeV or 3 GeV or 1 GeV. Some people want to push to the 1 GeV, they can argue, now gluon distribution be negative, all these things. No, so you have data, you have factorized formula, you do the fit, eventually find the inconsistency between the different observable. you lose the universality. That means the region of data is picking up from that have a problem. So that means it's not dominated by leading twist anymore. So the power correction becomes important. For the TMD case, as I say, you just nicely measure the PT distribution. That's what I told JLab experiment colleague. We have a theory experiment dialogue. Then, so when I say to them, you measure nicely PT distributions, don't artificial cut. They do best that they can. Then theory will give you the formula beside, in addition to the TMD, really nicely matched to the perturbed fixed order calculating formulas. Then we have a phenomenology to the global fit. But this is a harder problem. But of course, you can always start with a simpler problem. You artificially cut off some data, say, oh, TMD might work, do some tests, do some fit, whether it's reasonable. Because error bar is so big at the moment, the data error bar is big, everything seems to fit. But in the long term, just like LGC did, think about it, 15 order of magnitude of a cross-section, you have one set universal Poisson distributions. It's amazing. I started my career a long time ago, started as a member of CTEC collaboration as a postdoc. Then we did a lot of global fit. I did a lot of global fit too. But that time, the error bar is big. But now it's to the level. It's completely different now. But the TMD, we are not there yet. As I say, it's a long way to go. But on the other hand, it's a much richer physics than PDF, because PDF, in a sense, you integrate most interesting dynamics into the effective probability. But depend on interest, because you're interested in more high-scale observable. But if you're really interested in structural, non-perturbative physics, then you are more interested in the region, a mixture of TMD and the collinear.
Okay, thank you. You're very clear.
Okay, thank you very much. I don't see any other question actually from not even in the chat. So we probably can conclude the last lecture of introduction to QCD, and thank you very much for the very interesting lecture, John Wei. And I think we can meet again at the Axe Social at 4:30 p.m. on Gather Town. And maybe there was Aruns that wanted to add something. I don't know.
I don't know. What I try to tell the students, if they're interested, my last lectures have a lot of backup slides that give a lot of information on the spin physics. So those are very useful. It's very elementary. Most of them are just quantum mechanics. But there is one very important message is that when you talk about transfer spin, non-relativistic and the relativistic are very, very different. That message, remember that. And another is a tool, how to apply parity time reversal invariance when you're dealing with operators. So those are very useful when you're dealing with the spin physics.
Yeah, definitely. And we will also have the recap lesson tomorrow, right? So we'll talk about it again. And Arun, please.
Yes, actually, John Wei, I had a quick question also now that you mentioned this. I was wondering what how the QCD Lagrangian will change with the most recent discovery of the orderon. If it changes the QCD Lagrangian at all, or
well, at the moment, I think more studies needed about the orderon, because the orderon can be a composite state. But in the sense you can imagine it's a 3-gluon state. So then it's sometime when we first in the early 90s talk about the single spin symmetry, it's for the gluon channel is an interference between a single gluon and a 2-gluon composite state. Then you end up with get a single spin symmetry. It's in a sense dominated by a 3-gluon state. Then 3-gluon combination. So depending on the exact nature of the orderon, people talk about permeron. Permeron is dominated by a 2-gluon state. Then high state. So in a sense, if it's really as a composite state of the gluon, then we don't have to change the Lagrangian. It's just a part of QCD. It's an emerging phenomenon. Then if there is a really separate part, it's in some sense, we discovered the new pion, despite the proton, they are composite state of the QCD. We didn't change the QCD. Unless there is a really different part of QCD, or the additional part gave a very unique orderon feature. But as I say, we like to learn more from experiment, what the property of that or nature of them. I mentioned, permaron, we talked about many times, is a two-gluon, effectively two-gluon state, or two-gluon from sulfur-gluon state, but as a composite state, part of QCD. That alderon could be a part of QCD as well. But we don't know the features, right?
Right.
Yeah.
Okay, so that was my question, and I just want to make a quick announcement about the job interviews. Okay, so these are mock job interviews that we are conducting for HUGS students. Okay, there are 4 different job application postings that have been made on the HUGS website, one for theory postdoc, and one for experimental postdoc, another one for medical physics job, and I think one for industry position. So the deadline for these jobs are on the 11th, okay, June 11th. So we have roughly 8 days to 8.5 days to put together your application. And so you can either submit it. We have a link for the Google Drive. You can go to that folder and submit it in that folder itself. But if you choose that your application should be private, just either contact either myself, Astrid, or Juan, and we could put it in there, or forward your application to the persons who are going to interview you, or just submit it to that Google folder and mention to us that you don't want it to be viewed by your peers. But this is supposed to be one of the fun exercises of HUGS that it worked out really well for us last year. You go and sit and position yourself in that kind of an environment, and you actually potential hirers who have hired many postdocs and staff and people outside in the industry who have hired people. They come to interview you, and they look at your application and give you direct feedback as to how you could improve on that application. And as a theorist and experimentalist, we're always focused on our project and doing the best job that we can. But it'd be nice to get some feedback on how you can make your application robust as well. So that's the June 11th is the deadline for submission for those, and more information is going to follow through our emails. Okay, so that was it, Filippo.
Okay, thank you, Arun. And thank you, John Wei. We'll see you again tomorrow at 4:30 for the recap lesson.
Same link or different link?
It will be on Blue Jeans, actually. We'll send you the link. Yes,
Okay.
we will use just because it's more internal, the recap session. And you will actually use the whiteboard, right? So you will be at the lab probably. Or
Yeah, probably it's better for me. I saw the email from Alberta. I will go to the lab so I can use the whiteboard on the lab. Yeah.
Okay.
Tomorrow. Yeah.
That's perfect. And for the others, let's meet again for the Axe Social on Gather Town in 20 minutes. Okay. See you soon. Bye.
Bye.